What if the world we live in was shaped by machines older than history remembers? What if steam, gears, and coded numbers were already part of human life, 2,000 years before the modern age began? This is not science fiction. This is the legacy of ancient Greece. Before we begin, comment below where in the world are you listening from, and what time is it right now where you are? Because across oceans and time zones, we're about to journey together into a past that still shapes our present. Close your eyes, let the past unfold slowly, and listen to the story of the world's first true inventors. Now, let's begin. Before the hum of machines, before the ticking of clock, there was only silence, and the soft rhythm of questions forming in the minds of early thinkers. In a sunlit corner of the Mediterranean, the people began asking, what is motion? What is number? What lies beyond the stars and beneath the waves? This was ancient Greece, and their answers would shape the world forever. The Greeks did not invent electricity. They did not build spacecraft or split atoms. But what they did build were the first principles, the foundations of logic, mathematics, physics, and design. They constructed machines, not of steel and circuits, but of thought, gears, steam, and water. And perhaps most astonishingly, they did it over 2,000 years ago. To understand how this was possible, we must first understand the environment that nurtured this kind of genius. Ancient Greece was not a single nation. It was a constellation of independent city-states: Athens, Sparta, Corinth, Rhodes, and many others, each with its own government, military, and way of life. But what they shared was language, culture, and a deep reverence for inquiry. Education was not confined to the elite. In many cities, even common citizens could engage in debate, philosophy, and learning. In Athens, for instance, open discussion in the agora, the public marketplace, was routine. Ideas flowed as freely as water. No question was off limits. And unlike in many earlier civilizations, the Greeks didn't just seek to describe the world. They sought to explain it. Why does water flow downhill? Why does the moon change shape? Can numbers describe the universe? These weren't just poetic musings, they were problems to be solved, using reason, observation, and experiment. The earliest spark of this scientific spirit can be traced to Thales of Miletus, a philosopher who lived in the 6th century BCE. Thales is considered the first person in history to propose that natural events like earthquake eclipses have natural causes, not supernatural ones. He believed that everything came from water, not in a literal sense, but as a unified substance that underlies all things. More importantly, he tried to measure things. Thales is said to have predicted a solar eclipse and calculated the height of the Egyptian pyramids using only shadows and geometry. A man with no telescope, no calculator, just a stick and a mind unafraid of the unknown. He laid the foundation for a new way of thinking, one where nature was a puzzle, not a mystery, and it wasn't long before others followed. Next came Pythagoras. His name echoes through every math classroom today, but few know that Pythagoras also founded a brotherhood, a secretive order that viewed numbers as sacred truths. To Pythagoras and his followers, mathematics was not just a tool, it was the language of reality itself. They believed that harmony in music, patterns in nature, and proportions in architecture all stemmed from numbers. From this worldview, they uncovered the Pythagorean theorem, A tether plus B tether equals C tether, which allowed the precise measurement of space. But more than that, they revealed that the universe had structure, that geometry could describe form, and that abstract ideas could have real-world consequences. This would inspire generations of engineers to come. Fast forward to Athens, in the time of Socrates, Plato, and Aristotle, thinkers who didn't just look outward at the stars and machines, but inward, toward logic, ethics, and the nature of thought itself. Plato founded the Academy. Aristotle, his student, founded the Lyceum. Together they laid out systems of classification, logic, physics, and biology, creating the first frameworks for scientific thought. Aristotle, in particular, made detailed observations of nature. He studied animals, anatomy, weather, and motion. Though many of his conclusions were later corrected, his methods, careful observation and classification, became the groundwork for empirical science. He asked, what causes motion? What is time? What is the soul? And in each question, he saw a chance not to accept, but to investigate. But philosophy alone does not build machines. What transformed Greek thinking into technology was a revolution in practical knowledge. Enter Archimedes of Syracuse. Born in the 3rd century BCE, Archimedes was a mathematician, physicist, inventor, and engineer. He is said to have leapt from a bath shouting "Eureka!" after discovering the principle of buoyancy, but his contributions go far deeper. He invented war machines to defend his city, catapults, pulleys, mirrors to burn ships. He designed water screws for irrigation. He calculated areas, volumes, and surface areas with stunning accuracy, essentially inventing integral calculus 2 millennia early. His writings on levers include the legendary phrase, "Give me a place to stand, and I will move the earth." And then there was Heron of Alexandria, a mysterious figure from the 1st century CE. Heron wrote detailed manuals on automata, self-operating machines. He described devices powered by steam, water, air pressure, and counterweights. He built a steam-powered device called the Aeolipola, essentially the world's first engine. It spun when heated, and though it was treated as a novelty at the time, it foreshadowed the Industrial Revolution. Heron also designed vending machines, automatic doors, and theatrical stage effects. These weren't just ideas, they were real machines, built in temples and theaters, designed to evoke awe, wonder, and belief in divine magic. But they were powered by science. And yet, as the centuries passed, many of these inventions were lost. The fall of the Greek city-states, the burning of the Library of Alexandria, and the slow erosion of classical knowledge through wars and upheavals all contributed to the disappearance of these ideas from the Western world. But they did not vanish completely. Many Greek texts were preserved by scholars in the Islamic Golden Age and later reintroduced to Europe during the Renaissance. In that moment of rediscovery, Leonardo da Vinci, Copernicus, Galileo, and Newton all drew upon the ancient insights of the Greeks. The gears turned once more, not as myths, but as mechanisms. So tonight, as we begin our slow journey, remember that every law of physics, every machine, every algorithm has a lineage, and many of those lineages begin here, with scrolls and compasses, with questions and curiosity, with minds brave enough to ask, what is the world made of? Chapter 2. Archimedes, the mathematician who could move the earth. Imagine a city surrounded by sea, white stones, shadows cast by the late sun, and deep inside a quiet study, the man is drawing spirals in the sand. His name is Archimedes, and his mind would bend the world. Born around the year 287 before the Common Era, in the city of Syracuse, on the island of Sicily, Archimedes would grow to become one of the most influential thinkers in human history. He was not only a mathematician, he was an inventor, an engineer, a physicist, and a problem solver. Syracuse, though part of the Greek world, was far from Athens. It was a wealthy city, a hub of trade, surrounded by water and fortified with thick stone walls. Archimedes grew up in an educated family. His father was an astronomer, and from an early age, Archimedes was immersed in numbers, shapes, and stars. He studied in Alexandria, where he likely encountered the works of Euclid, but it was in his home city that his genius would take root, and it all began with a bath. Legend says that Archimedes was stepping into a full tub. As his body sank into the water, he noticed how the water level rose, and in that simple moment, a question became an answer. He realized that any object placed in water is pushed upward by a force equal to the weight of the water it displaces. This became known as the principle of buoyancy, or what we now call Archimedes' principle. In other words, if a crown made of gold is dipped into water, and the water it pushes away is weighed, you can determine if the crown is pure or mixed with other metals. This allowed him to solve a famous problem, detecting fraud in a crown without cutting it open. He was so thrilled by this discovery, he ran through the streets shouting "Eureka!", which means "I have found it." But this was just the beginning. Archimedes didn't only care about floating things, he cared about how things moved, how things could be lifted, how force could be multiplied. And from that curiosity came the concept of the lever. He showed that a small force applied at a long distance can move a large object, sitting close to the pivot point. To explain it in TTS-friendly terms, if a beam is balanced on a point, and you apply a force on one side at a longer distance, that force is amplified. This principle led him to say, "Give me a place to stand, and I will move the earth." He wasn't exaggerating. He understood mechanical advantage, how geometry and physics could turn effort into power. This led Archimedes to design machines, not just on paper, but real ones, used in battle. When the Roman army laid siege to Syracuse, Archimedes was asked to help defend the city, and he did. He built catapults with precise aim. He designed massive cranes to lift and drop enemy ships. He is even said to have used mirrors to focus sunlight and set Roman ships ablaze. Though this last tale may be myth, the others were very real and incredibly effective. Syracuse held off the Romans for years, thanks to the mind of one man. Beyond warfare, Archimedes also cared deeply about pure mathematics. He was fascinated by curves, shapes, and volumes. By the question, how do you measure the size of something that isn't a perfect square? He worked with parabolas, circles, and spheres, and he developed methods to approximate their area and volume, long before modern calculus existed. For example, to find the area under a curve, he would divide it into many tiny sections, then add them all together. This approach, though primitive, was the foundation of what we now call integral calculus. He found that the volume of a sphere is 2/3 the volume of the cylinder that surrounds it, and that the surface area of a sphere is also 2/3 that of the same cylinder. He was so proud of this discovery that he asked for a sphere and a cylinder to be carved on his tombstone. Archimedes also invented a device still used today, the Archimedean screw. It is a simple machine, a spiral-shaped blade inside a hollow cylinder. When you turn it, it lifts water upward. It was used to move water for farming and irrigation, and the same principle is now used in some modern pumps and turbines. This wasn't theory, this was practicality, a device that changed how humans viewed water with elegance and efficiency. His writings were vast, and many of them survived. He wrote about floating bodies, balancing planes, and methods for counting grains of sand that could fill the universe. Yes, he even attempted to estimate the size of the cosmos using powers of numbers far beyond the Greek counting system. He invented a way to express huge quantities, the beginnings of what we now call exponential notation. For instance, instead of just counting by ones, he grouped numbers in powers of 10,000. This allowed him to estimate the number of sand grains that would fill a sphere the size of the known universe. It was both poetic and mathematical. But Archimedes' life ended not in a lab, but in war. When the Romans finally breached Syracuse, the general Marcellus ordered that Archimedes be captured alive. He valued the man's genius, but the soldiers did not recognize him. They found him drawing in the sand, lost in thought. He told them, "Do not disturb my circles," and for that, he was killed. A brilliant life ended in silence. Yet Archimedes' influence only grew with time. Centuries later, his writings inspired Galileo, Newton, and many others. They saw in his words not just math, but insight, a vision of the world that connected motion, matter, and mind. He was not just a Greek thinker, he was the beginning of engineering. He proved that thought could move stone, that logic could build machines, that one mind deep in the ancient world could stretch forward into eternity. Chapter 3. The Antikythera Mechanism, the world's first computer. Deep beneath the blue waters of the Aegean Sea, just off the coast of a small Greek island, a mystery lay buried for 2,000 years. It was not a statue, not a shipwreck filled with gold, but something far stranger, a bronze machine, with gears, inscriptions, and secrets no one understood. They called it the Antikythera Mechanism, and what they found should not have existed. The story begins in the year 1900. A group of sponge divers from the island of Syme were caught in a sudden storm near the island of Antikythera, between mainland Greece and Crete. When the seas calmed, they dove down into the depths to search for sponges along the seafloor. Instead, they found a shipwreck, the remains of an ancient Roman cargo ship, filled with bronze statues, marble figures, amphorae, and a pile of corroded fragments that looked like twisted metal. Among them, one small lump of bronze, no larger than a shoebox, would change everything. It contained gears, and not just one or two. Dozens. Perfectly cut, precise, mechanical. The divers had no idea what they'd found. Neither did the archaeologists at first. It would take decades to understand what this ancient machine truly was. They called it the Antikythera Mechanism, named after the island where it was found. For years, it sat in a museum in Athens, almost forgotten, corroded, unrecognizable. It wasn't until 1951 that a British historian named Derek de Sulla Price began studying it closely. Using X-ray imaging, he peered inside the corroded mass and saw something stunning: gears, wheels, inscriptions, a system of astonishing complexity built more than 2,000 years ago. This wasn't a toy, it was a machine with a purpose. So what did it do? As the pieces were slowly reassembled, a new picture emerged. The Antikythera Mechanism was a kind of analog computer built to predict astronomical positions and eclipses. It could show the phases of the moon, the movement of the sun and planets, and the dates of solar and lunar eclipses, years in advance, all using bronze gears and hand-powered cranks. No electricity, no screen, just mathematics, in metal. It could even track the Metonic cycle, a period of 19 years after which the phases of the moon repeat on the same days of the year, and the Saros cycle, used to predict eclipses. Some gears were so finely cut, they had over 200 teeth, shaped and spaced with mathematical precision. It was, in effect, a mechanical model of the heavens. But here's the real mystery. This machine was built sometime between 150 and 100 before the Common Era. That's over 2,000 years ago. Nothing like it would be built again until the mechanical clocks of the 14th century. That's a gap of over 1,000 years. So the question is, who made it and how? Some clues point to Rhodes, an island known for its skilled metal workers and astronomers. One possible creator is Hipparchus, a Greek astronomer who lived in the 2nd century before the Common Era. He was the first to create a trigonometric table, and he accurately modeled the eccentric orbit of the moon. His work is consistent with the complexity of the mechanism. Others believe it may have come from Posidonius, another philosopher and astronomer from Rhodes, who had a school known for its advanced celestial models. Whoever built it, they combined deep knowledge of astronomy, mathematics, metallurgy, and mechanical engineering, all in a device no larger than a briefcase. The mechanism had front and back dials. On the front, it showed the position of the sun and moon in the zodiac. It even included a calendar. On the back, 2 spiral dials. The upper spiral showed the Metonic cycle of 19 years. The lower spiral tracked the Saros cycle of eclipses, each one marked with Greek inscriptions. Turn a handle, and the mechanism would show the sky, not as it was, but as it would be. It could simulate the night sky in the past or future, a tool for priests, sailors, philosophers, or all three. But it wasn't just a tool, it was also a statement. It said, the universe follows rules, the heavens can be measured, time can be calculated. This was technology as philosophy, a mechanical model of cosmic order, built not to impress kings, but to understand the cosmos. It represents the very soul of ancient Greek thinking, a belief that knowledge is beautiful and worth building into bronze. So why was it art? We don't know how many of these machines were made. This could have been one of many, or the only one. What we do know is that after the Roman conquest of Greece, much of this knowledge was forgotten. The Library of Alexandria, where blueprints may have once existed, burned, empires rose and fell, and the gears of understanding slowed. The Antikythera Mechanism sank with its ship, and with it, 1,000 years of silence. It wasn't until 21st century imaging that scientists truly began to decode the full structure. Using 3D X-ray tomography and advanced surface imaging, researchers discovered that the mechanism had at least 37 gears, possibly more, each one cut by hand, each tooth carved precisely. Some were epicyclic gears, small gears rotating on larger ones to model complex planetary paths. This was not a toy, it was a scientific instrument, and it used math that wouldn't be formalized until the Renaissance. Its construction raises a deeper question: how much ancient knowledge have we lost? If this one machine survived only by accident, what else once existed? What machines, diagrams, inventions have vanished beneath centuries of war, erosion, and neglect? The Antikythera Mechanism reminds us that the ancient Greeks didn't just ask questions, they built answers. Answers made of bronze, gears, and genius. Today, replicas of the mechanism exist. They sit in museums and universities, Some are even 3D printed, not because we need them to track the moon, but because they humble us. They remind us that 2,000 years ago, without computers or factories, someone looked up at the sky and said, "I can build this." Oh. So tonight, as you close your eyes, picture the device resting in its glass case, silent, precise, beautiful. A lost computer that never needed electricity, only time, patience and vision. Chapter 4: Heron of Alexandria. Steam power before its time. In the bustling heart of ancient Alexandria, a city of marble libraries, stone temples, and open-air theatres, lived a man whose mind played with fire, air, and metal. His name was Heron, and long before the Industrial Age, he built machines powered by steam. Not stories, not sketches, but real, working devices. He lived in the 1st century of the Common Era, during the peak of Roman Egypt, at a time when Alexandria was the intellectual center of the world, and yet, what he built would not be understood for nearly 2,000 years. We know Heron, also called Hero of Alexandria, primarily through his writings. Dozens of manuscripts survived, describing mechanical wonders, geometrical theories, and practical devices. He wasn't just a philosopher, he was an engineer. He wanted to show that the forces of nature, steam, pressure, gravity, air, could be harnessed with mathematics. In a temple, he would see fire and imagine a door that opens itself. He would see a boiling pot and imagine a spinning sphere where others saw heat. He saw potential energy. His most famous invention was called the Aeolipola. It is widely considered to be the first recorded steam engine in history. Imagine this: a metal sphere suspended by arms, with 2 small bent tubes on opposite sides. Fill the sphere with water, light a fire beneath it. As the water heats, steam builds inside and escapes through the tubes. The escaping steam creates thrust, and the sphere begins to spin. A reaction engine, fueled by nothing but water and fire. It didn't power factories, it didn't pull carts, but it worked. It showed the concept. It was proof of principle. Heron's writings were full of such devices. In one of his books, he described a system for automatically opening temple doors. It worked like this: a fire would be lit on an altar. The heat would build pressure in a sealed vessel beneath the altar. This pressure would push water into a second container. That water, in turn, would shift a system of pulleys and counterweights, and the temple doors would slowly swing open. To the average person, it looked like magic. Fire summoned the gods, and the doors obeyed. But in truth, it was pure engineering. The use of air pressure, vacuum heat expansion, and hydraulics all combined to create an automatic system. This wasn't entertainment, this was automation. Heron also described a coin-operated vending machine. Yes, in the 1st century, you could drop a coin into a slot and receive holy water. Here's how it worked. The coin would fall onto a small lever. That lever opened a valve. Water flowed out. Once the coin tipped off the lever, the valve closed. It may seem simple, but this is the core mechanism behind vending machines today. Input, trigger, delivery, reset. The logic is identical. He applied the same thinking to other machines: fountains, fire starters, siphons, pressure systems. His work was deeply rooted in physics. One of Heron's most fascinating texts is called Automata. In it, he described devices used in theatrical performances: moving puppets, mechanical birds, stage effects controlled by ropes, pulleys, gears and weights. In one account, he detailed a miniature theater show that ran for 10 minutes, completely self-operating. No humans behind the curtain, just precision mechanisms, set in motion by gravity and careful design. The entire performance was programmed, like a mechanical script. Today, we would call this a programmable machine. He understood feedback, he understood flow control, he understood storage of energy and timed release. These are not just mechanical tricks, they are foundational principles of robotics. He called them automata, we call them prototypes. Heron may not have imagined robots walking and talking, but he knew machines could mimic life. And he built them with nothing but tools of the 1st century. Heron also wrote mathematical texts. In one of them, he introduced Heron's formula. a way to calculate the area of a triangle when you know the lengths of all three sides. The formula is simple in words. Take the semi-perimeter, which is half the sum of the three sides. Then subtract each side from that semi-perimeter. Multiply the semi-perimeter by each of those three results. Then take the square root of the entire product. This gave an exact area without needing to know the height of the triangle. It's elegant, it's useful, and it's still taught today. But perhaps Heron's greatest gift was his way of thinking. He believed that nature obeys patterns, that mechanics is not sorcery, it's science, and he believed that human hands, guided by reason, could copy those patterns. That belief shaped how later civilizations saw machines. Even though his work was forgotten for centuries, it resurfaced during the Islamic Golden Age, and again in the Renaissance. Thinkers like Leonardo da Vinci studied his books. Engineers built on his designs. The principles of pneumatics, hydraulics, and steam all trace back to Heron's manuscripts. So why didn't Heron's steam engine start an industrial revolution? The answer may lie in context. Ancient societies didn't have the economic or political structure to mass-produce machines. Slavery was common, labor was cheap. There was little incentive to replace humans with engines. In other words, the technology was ready, but the world was not. So Heron's Aeolipalail remained a demonstration, a marvel, a symbol of what was possible, but not yet necessary. Still, his legacy remains profound. In Heron, we see the roots of a future that wouldn't bloom for nearly 2,000 years. We see the first steps toward automation, the first glimmer of machine logic, the first realization that forces, steam, air, heat could be controlled, not by magic, but by mind. So, as you rest tonight, think of a small sphere spinning quietly in an ancient temple, steam escaping through tiny pipes, gears turning, doors opening, crowds gasping, and in the shadows, a man with ink-stained hands, smiling quietly to himself, not for fame, not for wealth, but for the joy of knowing that nature had rules, and he could write them in metal. Chapter 5. The Mathematics of Euclid and Pythagoras. Before steel, before engines, before anything could be built, there had to be geometry, not as a tool, but as a way of seeing, a silent system underneath shapes, motion, and form, a truth that did not shift with opinion or time. And in the ancient world, no two names carved that system more deeply than Pythagoras and Euclid. They didn't forge machines, they forged logic, and in doing so, they created the blueprint for all that would follow. Let us begin with Pythagoras. He was born around the year 570 before the Common Era, on the island of Samos in the Aegean Sea. Though little of his original writing survive, his influence has rippled through centuries, not just in mathematics, but in music, philosophy, and even mysticism. To Pythagoras, numbers were not just quantities, they were principles, sacred patterns that echoed through reality. He believed the universe was made of ratios, relationships between numbers, and that those relationships created harmony. In music, he discovered that plucking strings of different lengths produced notes in perfect mathematical proportion. A string half the length of another produced a tone exactly one octave higher. This insight that music obeyed mathematics was a revelation. It meant that beauty, order, and even sound could be described with numbers. To Pythagoras and his followers, the world wasn't chaotic, it was a geometric structure, built from silent laws. And from this view came one of the most famous discoveries in history, the Pythagorean theorem. In TTS-friendly terms, if you have a triangle with a right angle, and you know the length of the two shorter sides, you can find the length of the longest side called the hypotenuse by squaring each of the short sides, adding those squares together, and then finding the square root of that sum. For example, if one short side is 3 units long and the other is 4 units long, you multiply 3 by 3, which gives you 9, then multiply 4 by 4, which gives you 16. Add them together, you get 25. Now take the square root of 25. That gives you 5, which is the length of Archimedes. This formula works for all right triangles, and it changed everything. Builders used it to create straight angles in temples. Surveyors used it to divide land. Engineers would later use it in machines, bridges, and towers. But Pythagoras' ideas went deeper. He and his students, called the Pythagoreans, believed in something more profound. They believed the universe was They studied polygonal numbers, explored the golden ratio, and considered mathematics to be a path to spiritual enlightenment. To them, understanding shape was understanding existence. Yet their ideas, while powerful, were often secretive. The Pythagorean school was almost cult-like, private, symbolic, closed to outsiders. But in the centuries that followed, another man would take those mystical fragments and turn them into a logical, open system. His name was Euclid. Euclid lived around the year 300 before the Common Era, most likely in the city of Alexandria, in Egypt. While Pythagoras worked with discovery, Euclid worked with proof. He wasn't searching for patterns in nature, he was building an axiomatic system, a step-by-step structure for mathematics. His most famous work is called The Elements. It is not a story, it is a system, a structured layout of over 400 propositions, built from just a few starting definitions. The Elements is composed of 13 books, each one builds on the previous. It begins with definitions. For example, a point is that which has no part. A line is breadthless length. A straight line is a line which lies evenly with the points on itself. Then it introduces postulates, statements assumed to be true. One of the most famous is, a straight line can be drawn between any two points, and all right angles are equal to one another. From these definitions and assumptions, Euclid begins to construct geometry. He proves theorems, not by guessing or measuring, but by deduction, step-by-step logic. This was revolutionary. Euclid wasn't just teaching shapes, he was teaching reasoning. Let's consider a famous proposition. The sum of the interior angles of a triangle is equal to 2 right angles. Or in modern terms, the sum of the 3 angles inside a triangle is always 180 degrees. Euclid didn't just state this, he proved it, using parallel lines, alternate angles and logical steps. This showed that geometry could be built like a machine, each part depending on the last, each statement supported by the structure beneath it. In a way, Euclid had invented mathematical architecture, but his influence goes even further. The Elements was used as a textbook for over 2,000 years. It was taught in schools across the Greek, Roman, Islamic, and European worlds. It was translated into Arabic, Latin, and many other languages. It shaped the way scientists and engineers thought. Galileo, Newton, Descartes, all were trained with Euclid's logic. Even today, in every geometry class, we still use the basic format he created: definitions, postulates, proofs. It's not just the contents, the structure of thinking that Euclid gave us. Euclid also laid the groundwork for number theory. He explored the concept of prime numbers, numbers that are only divisible by 1 and themselves. He proved that there is no largest prime number, that primes go on forever, and he offered a method to find the greatest common divisor of any two numbers. This method is still used today. It's called the Euclidean algorithm. It's how modern computers simplify fractions, and it plays a role in encryption systems used in technology. Euclid's fingerprints are still in our code. So what was the legacy of these two men? Pythagoras gave us the intuition of numbers, the sense that reality has harmony, proportion, rhythm. Euclid gave us the method of structure, a system to prove, verify, and explain that harmony. Together, they built a foundation for geometry, architecture, physics, and engineering. Without them, there would be no clear rules for space, no way to describe form, no method to build. Look around any city today. Every bridge, building, road, and dome is traced back to lines and angles, to ratios, to triangles, to circles, to Pythagoras and Euclid. They may not have laid stones, but they told us how to lay them, and more importantly, why they would stand. They made space understandable and gave future civilizations a toolkit for thinking in structure. So tonight, as you rest in silence, know that the shapes around you, the walls, the beams, the ceiling above, all whisper the same silent truths. Lines that never end, angles that always add, the logic of space, quietly holding up the world. Chapter 6, Greek Astronomy. The universe in circles and spheres. Before telescopes, before satellites, before we even knew what stars were made of, the ancient Greeks were already watching the skies, carefully, patiently, night after night, and from those silent observations, they built something extraordinary, the first real models of the universe. Not just maps, but mathematical systems describing how the heavens moved and why they moved the way they did. They believed the cosmos was a kind of music, played out in perfect invisible circles. And though they would be proven wrong in many details, they were right about something much deeper, that the universe follows laws, and those laws can be discovered. The Greek word for world was cosmos. It meant not just the universe, but order, arrangement, beauty. To the Greeks, the night sky was not random. It was a great clock, a system of rotations and cycles. They saw the stars move across the sky every night. They saw the sun rise and set. They watched the phases of the moon and the strange dance of 5 bright planets. They observed eclipses. They timed the solstices. They tracked the shifting positions of constellations, and slowly, carefully, they built models. The earliest known astronomer in the Greek tradition was Thales of Miletus. He lived in the 6th century before the Common Era. Thales was said to have predicted a solar eclipse. He proposed that celestial events might have natural causes, not divine ones. He introduced the idea that the universe could be understood, not just worshipped. His student Anaximander tried to describe the heavens using circular wheels of fire, an early attempt to imagine 3-dimensional space, though inaccurate. It was bold, a step toward natural explanation. But the real breakthroughs came later, in the 5th and 4th centuries before the Common Era. The philosopher Eudoxus of Cnidus proposed the first serious mathematical model of the universe. He used nested spheres, each one rotating in a different direction. He imagined the Earth at the center, surrounded by a system of concentric, transparent spheres. Each sphere carried a planet, the sun, or the moon. As they rotated, they created the observed motions in the sky to explain the path of a single planet. Eudoxus used 4 spheres. In total, he needed 27 spheres to explain all the known celestial movements. This was the first time anyone had built a geometric model to explain planetary motion. It wasn't perfect, but it was a system, a way of predicting the heavens using math. Then came Aristotle. He accepted Eudoxus' model, but expanded it. He argued that the heavens were made of a perfect substance, called the aether. Unlike anything found on Earth, he believed celestial bodies moved in perfect circles, at constant speeds, because that was the most natural motion. Aristotle added new spheres, eventually totaling 55. These spheres were not just geometrical ideas. To him, they were real, crystalline shells, turning around the Earth. This geocentric model, Earth at the center, would remain dominant for nearly 2,000 years. Even when it was wrong, it was organized, and that structure made progress possible. But no one advanced astronomy more dramatically than a man named Hipparchus. He lived in the 2nd century before the Common Era, and he brought precision to the stars. Hipparchus made incredibly detailed star charts. He catalogued over 1,000 stars, assigning them coordinates based on longitude and latitude in the sky. He measured the length of a year with remarkable accuracy. He also discovered something extraordinary, that the Earth's axis was slowly shifting over time. This is called precession, and it takes over 25,000 years to complete a full cycle. Hipparchus discovered it by comparing his data to records from Babylonia centuries earlier. He even developed a mathematical model for the motion of the moon, accurately enough to predict solar eclipses. His work laid the foundation for the most influential astronomer of ancient Greece, Claudius Ptolemy. Ptolemy lived in Alexandria in the 2nd century of the Common Era. His most important work is called the Almagest, a 13-book treatise on astronomy. In it, Ptolemy adopted the geocentric model, Earth at the center, but refined it with a new system, epicycles. Here's how it worked. In TTS-friendly terms, each planet moved in a small circle, called an epicycle. That small circle itself moved along a larger circle, called the different, which was centered around the Earth. This created a looping path, explaining why planets sometimes appear to move backward in the sky, a phenomenon called retrograde motion. Ptolemy added another twist. He placed the Earth slightly off-center in his model, to better match observations. Though the system was complex, it worked. It accurately predicted planetary positions, and it remained the dominant model for nearly 1,500 years. Ptolemy also described the phases of the moon, the length of seasons, and explained how eclipses occurred, using geometric shadow models. His model was not physically correct, but it was mathematically useful. It allowed calendars to be refined, sailors to navigate, and time to be measured. And in an era with no telescope, that was extraordinary. So what did the Greeks really understand about the cosmos? They believed the Earth was a sphere. They calculated its size with surprising accuracy. The philosopher Eratosthenes did this in the 3rd century before the Common Era. He noticed that on the summer solstice, the sun shone directly down a well in the city of Syene, but on the same day in Alexandria, it cast a shadow. Using the angle of the shadow and the distance between the cities, he used geometry to estimate the Earth's circumference. His result was very close to the real value. The Greeks knew the moon was spherical, based on its shadow during lunar eclipses. They knew the moon's light came from the sun. They understood the relationship between the sun's position and the seasons. They even considered the possibility that the Earth might move, though that idea would not take hold until much later. But even with incorrect assumptions like circular orbits, they were asking the right questions. They were seeking patterns. They were building models. They were testing predictions. They invented mathematical astronomy, and that changed everything. Centuries later, when Copernicus proposed a heliocentric model, he still used Ptolemy's epicycles. When Kepler adjusted those orbits into ellipses, he built on data inspired by Hipparchus. And when Newton wrote the law of gravity, he united the mathematics of motion with the questions first asked in Greek observatories. So tonight, as the stars drift overhead, imagine ancient scholars lying beneath the same sky, drawing arcs with string, marking angles in sand, counting shadows, measuring time by light. They could not see planets clearly, but they knew they moved. They had no rockets, but they built orbits on paper. They had no computers, but they constructed cosmic machinery with numbers. They gave us the first models of the universe, not as myth, but as math. Chapter 7. Medicine before modernity. Hippocrates and early surgical tools. The stars above fascinated the Greeks, but they were just as curious about the world beneath the skin. How does the body heal? Why does it break? What causes pain, fever, or death? These weren't questions for oracles anymore. They were questions for doctors. In ancient Greece, a new idea began to form, that illness was not punishment from the gods, but the result of natural causes, and to treat it, one needed not ritual, but reason, observation, and hands skilled in healing. The name most closely tied to this revolution in medicine is Hippocrates, born around the year 460 before the Common Era, on the island of Kos. Hippocrates is often called the father of Western medicine, and while the title is grand, it's not undeserved. He didn't invent surgery, he didn't discover germs, but he did something that would change medicine forever. He separated it from superstition. He proposed that disease had physical causes, that the body followed laws just like the stars did, and that those laws could be studied. Before Hippocrates, many illnesses were blamed on the gods. Epilepsy was called the sacred disease. Fevers were seen as divine punishments. Hippocrates rejected this. He believed disease came from imbalance within the body, specifically an imbalance of 4 fluids called the humors: blood, phlegm, yellow bile, black bile. Each humor was linked to an element, a season, and a temperament. Though the theory was wrong, it was the first system to describe illness in human terms, as a pattern, as a process, not as fate. More importantly, it allowed doctors to begin examining, recording, and comparing cases of illness. This was the birth of clinical observation. Hippocrates and his students recorded their knowledge in a collection of texts, now called the Hippocratic Corpus. These writings covered everything from diagnosis to prognosis to ethical practice. They included detailed case studies, descriptions of symptoms, recommendations for diet, rest, and cleanliness. One core principle stood out: do no harm. This was the seed of the Hippocratic Oath, a code of ethics that still influences medical practice today. It emphasized confidentiality, competence, and above all, respect for the patient. In a world where healers were often priests or magicians, this was a radical shift. Greek medicine was not just philosophy, it was practical. Doctors examined urine and stools. They checked pulse and temperature. They cleaned wounds, set bones, and drained abscesses. They used honey as an antiseptic, wine as a disinfectant, and herbal mixtures as pain relief. And in more serious cases, they performed surgery. With tools made of bronze and iron, Greek physicians developed early versions of instruments we still recognize today. They had scalpels, forceps, probes, curettes, catheters, and bone drills. Some were smooth and elegant, others were brutal by today's standards, but they were designed with precision. In the ancient city of Pergamon, archaeologists have uncovered a surgical kit from the 3rd century before the Common Era. It contained over 100 tools, laid out in an orderly case, some for cutting, some for cauterizing, others for stitching wounds. This wasn't improvised medicine. It was systematic. Greek doctors used these tools in battlefield surgeries, in treating infections, and even in simple cosmetic repairs. They understood anatomy, even without dissecting human corpses, which was considered taboo in most of Greece. Instead, they learned by watching wounds, examining injuries, and studying animals. Their knowledge was imperfect, but it was growing. The city of Alexandria, again, became a center for this growth. In the 3rd century before the Common Era, under the rule of the Ptolemies, Greek scholars in Alexandria were allowed to perform human dissection. This was a turning point. Doctors like Herophilos and Erasistratus began mapping the human body. They studied the brain, the nervous system, the circulatory system. Herophilos distinguished between sensory and motor nerves. He described the brain as the seat of thought, an insight centuries ahead of its time. Erasistratus explored the function of the heart, the pulse, and the flow of blood. Though they didn't discover circulation as we know it, they were among the first to treat the body as a mechanism. Greek medicine was deeply tied to diet and environment. Hippocrates believed that food, air, water, and lifestyle all influenced health. He encouraged moderation, rest when sick, fresh air, clean water, avoiding extremes of cold and heat. This may seem obvious now, but in ancient times, it was revolutionary to link health to daily living. Illness was not always a mystery. It was often a consequence, and it could sometimes be prevented. Greek doctors also developed methods of prognosis. Rather than simply reacting, they tried to predict the outcome of illness. This gave patients and families time to prepare or to adjust treatment. They described the stages of fevers, the patterns of infection, the turning points in disease. Their records show remarkable accuracy in describing conditions like pneumonia, tuberculosis, and wounds. They even described mental disorders, using terms like melancholia for depression. Though they lacked our chemical understanding, they knew the mind and body were connected. They saw healing as a process, not a miracle. Public health also mattered. Greek cities built aqueducts for clean water. They managed sewage and drainage. They understood the spread of disease in crowded areas. Doctors advised cities to build hospitals away from swamps, with fresh air and sunlight. While they didn't understand microbes, they understood conditions, and they used that understanding to reduce suffering. Medicine became not just personal, but civic. Many of these ideas were preserved, copied, and passed on. Later Greek doctors like Galen built on Hippocratic medicine. His writings dominated medieval medicine in both the East and West, and even as Rome rose and Greece declined, the medical system they started endured. Through Islamic scholars, Byzantine physicians, and Renaissance scientists, Greek medical texts remained alive. Translated into Arabic, then Latin, they formed the backbone of Western medical education for over 1,000 years, until modern science caught up and surpassed them. Their influence remained unmatched. So what did the Greeks really give us? Not antibiotic, not germ theory, not anesthesia, but something perhaps more powerful, a way of thinking. They gave us observation, pattern recognition, experiment, notes, care, compassion. They gave us the idea that medicine is a practice, one that can grow, improve, and serve. They gave us doctors, not just healers. So as you lie still tonight, think of the quiet hands that once wrapped bandages, mixed herbs, washed wounds, and whispered, "Let me help." They didn't have all the answers, but they asked the right questions, and that, more than anything, is how healing begins. Chapter 8: Hydraulics, Gears and Water Clocks. How Greeks Engineered Time. The ancient Greeks watched the stars to measure time, but they didn't stop there. They wanted time to flow, to tick, to move with rhythm like water through stone, so they built machines to make it real. Clocks powered not by springs, but by dripping water. Gears that turned not for show, but to calculate. They engineered time, and in doing so, they bridged the space between natural flow and mechanical precision. To understand how the Greeks engineered time, we begin with one idea: Hydraulics. Hydraulics is the science of using fluid pressure to create force or motion. Today, it powers construction equipment, airplanes and factory machines. But in ancient Greece, hydraulics began with something far simpler: gravity. Let water fall, catch it, control its flow, measure its pressure. This became a source of energy, measurement, and even automation. One of the earliest devices to harness this principle was the klepsydra, the Greek word for water thief. The klepsydra is a water clock. It worked like this. Water dripped slowly from one container into another. As the lower vessel filled, time was measured by the rising water level. Marks on the inner wall of the vessel showed how much time had passed. It was a silent clock, one drop at a time. Klepsydras were used in courts to time speeches, in temples to time rituals, and in daily life to regulate appointments. They weren't accurate by modern standards, but they represented a new mindset, that time could be tracked, not just experienced. Some water clocks became more complex. The Greeks added gears, floats, and indicator arms. Imagine a container slowly filling with water. Inside it, a floating disc rises with the water level. This float is attached to a vertical rod, which connects to a horizontal arm. As the float rises, the arm turns, pointing to a dial that shows the hour. This is mechanical timekeeping. It's not digital, it's not electric, but it's real. And it worked. These water clocks became more than tools. They were instruments, used by astronomers, priests, and engineers. One of the most advanced hydraulic engineers in Greece was Philon of Byzantium. In the 3rd century before the Common Era, he wrote a treatise called Pneumatics, describing machines powered by water, air, and pressure. Philon described valves that opened and closed automatically, nozzles that adjusted flow, and floats that triggered mechanisms when liquid reached a certain height. One of his inventions used a hidden reservoir of water to power a mechanical bird that chirped when people entered a temple. As water moved through chambers, air was forced through a whistle, creating a lifelike sound. This was engineering meets performance. Hydraulics also powered automation. In devices like the self-filling wine cup, a siphon system would refill the cup automatically when the level dropped below a certain point. This used basic principles of fluid balance and pressure gradients. Siphons were crucial. A siphon is a curved tube that allows liquid to flow uphill and then down, using only atmospheric pressure and gravity. It seems magical, but it's just physics. Greeks used siphons in fountains, irrigation, and even in defense to move liquids in secret ways. Another key development was the gear. Gears allowed circular motion to be transferred, slowed down, or sped up. By combining gears of different sizes, you could create systems of ratios where one turn of a large gear moved a smaller gear multiple times. This was the beginning of mechanical calculation. The Greeks used gears in many machines. One famous example is the Antikythera Mechanism, which we explored earlier. Its gear trains were precise, some with over 200 teeth, hand-cut to model lunar cycles and eclipses. But these gears weren't just used for the heavens. They also appeared in water clocks, where they helped control dials, arms, and indicators. The Greeks were already thinking in modular systems. In Alexandria, the engineer Ctesibius pushed hydraulic innovation even further. He created a regulating device, a float regulator that maintained constant water flow in klepsydras. This made water clocks far more accurate, because they no longer sped up or slowed down as pressure changed. He also built a water organ, an instrument that used air pressure and hydraulics to produce musical tones. The organ used bellows and valves to push air through tuned pipes, creating rich, resonant sound. It was music powered by fluid mechanics. These machines were not just toys, they were early versions of feedback systems. They used inputs, responses, and regulation. The same logic that runs in modern robotics and code. A float rose with water. It triggered a gear. The gear moved an arm. The arm pointed to a dial. That's a sequence, an analog program. The Greeks didn't call it programming, but that's what it was. A system that responds to change in a controlled, measurable way. We also find complex timekeeping machines in descriptions by Heron of Alexandria. In his automata, he used water flow and weights to trigger theatrical effects on cue. Imagine a miniature stage. As water slowly fills a chamber, a float rises. At a set height, it pulls a string. That string opens a curtain. A puppet appears. The music begins. All of this timed by water. No electronics, no batteries, just motion, mass and pressure. Heron even described a programmable cart, where pegs placed in slots could guide wheels and steer paths. Again, it's a form of mechanical logic. But why was all this possible? Because the Greeks didn't just observe nature, they believed it had structure. They watched how water moved downhill, how air expanded with heat, how pressure built behind a closed valve. Then they measured it, modeled it, and finally built with it. Hydraulic machines weren't just useful, they were philosophical. They showed that even invisible forces could be captured, channeled, and used. Time, they realized, was one of those forces. It flows, it fills, it empties, it changes everything, silently. These devices inspired later technology. Water clocks appeared in China, Persia, and Rome, sometimes with even greater complexity. Gears, floats, and pressure systems would re-emerge in medieval monasteries, in Islamic astronomical observatories, and later in the factories of the Industrial Revolution. The logic remained because the Greeks had already found it. They had already built it. So tonight, as you drift into sleep, imagine a dark stone chamber lit by a single oil lamp. In the corner, a small stream of water drips into a bowl. It rises, slowly, with time. A float begins to lift. A gear starts to turn. A bronze pointer moves, marking the hour. This is time, measured by water, built by hand, guided by thought. Chapter 9. Greek Architecture and Structural Physics. Building with Harmony. When you imagine ancient Greece, what do you see? Columns, temples, stone theatres under the open sky, shapes carved in white marble, still standing thousands of years later. These structures weren't just buildings. They were ideas, turned into matter, mathematics, made solid. The Greeks didn't build randomly. They built with purpose, with symmetry, with proportion. They built with logic. And Greek architecture wasn't only about shelter, it was about order. Each column, each beam, each space was placed deliberately, not just to hold weight, but to align with harmony. They used geometry as their blueprint, and physics as their silent partner. And over time, they developed a system of architecture that still shapes how we build today. This chapter is about that system, and how the Greeks used numbers, angles, and materials to shape the world around them. Let's begin with the most iconic form, the Greek temple. Temples were not just places of worship, they were models of perfection. Every part followed a system. There were no casual choices, only calculated elegance. The most well-known example is the Parthenon, built on the Acropolis in Athens between 447 and 432 before the Common Era. It was dedicated to Athena, the goddess of wisdom, and it remains a masterpiece of design. The basic elements of a Greek temple were the stylobate, the columns, the entablature, and the pediment. The stylobate was the platform, the slightly raised base that supported everything else. The columns rose from this base, fluted vertical shafts topped with capitals. Above the columns sat the entablature, a horizontal structure divided into three parts: the architrave, the frieze, and the cornice. At the top was the pediment, a triangular space often filled with sculptures. The proportions of each part were guided by ratios that came from geometry, not guesswork. The result was balance, the feeling that nothing was missing, and nothing was too much. Greek columns came in three major styles, called orders: Doric, Ionic, and Corinthian. The Doric order was the oldest and simplest. Thick columns, no base, a plain, rounded capital. It gave a sense of strength and stability. The Ionic order was more elegant, slimmer columns with bases, capitals with spiral scrolls called volutes. It was often used in smaller, more decorative buildings. The Corinthian order came later. It was the most ornate, with leafy floral carvings at the top. Though less common in classical Greece, it became popular during the Roman era. Each column followed a specific height-to-width ratio. In Doric temples, a column might be 5 to 6 times as tall as its diameter. In Ionic temples, the ratio might be 8 to 1. This gave each style a personality: heavy, graceful, or ornate. These ratios weren't just for looks, they also helped distribute loads, weight from the roof and upper structures. Columns were not solid all the way through. They were often built in drums, circular segments stacked on top of one another. Each drum was carved and aligned precisely. Gravity and friction held them together. No glue, no bolts, just balance. The Greeks understood that stone is strong under compression, but weak under tension. They designed their temples so that most forces pushed downward. This kept the weight aligned with the strength of the material. Roofs were pitched, angled to shed rainwater. Interior beams were placed strategically. Openings were limited to prevent stress on walls. These choices weren't accidental. They were informed by experience, experiment, and intuition refined over generations. One of the most brilliant aspects of Greek architecture was its optical correction. The Greeks realized that the human eye is not a perfect tool. When you look at a long, straight line like a temple floor, it may appear to sag in the middle. To correct for this illusion, Greek architects made the stylobate slightly convex, so it gently curves upward. Similarly, columns were made to bulge slightly in the middle, a feature called entasis. This made them appear straighter and more alive. Even the corner columns were spaced more closely, to correct for how we perceive light and shadow at the edges. In other words, they didn't just build what was mathematically straight, they built what would look straight to human eyes. This attention to perception is a hallmark of Greek design. Beyond temples, the Greeks also built amphitheaters. These were large open-air venues for plays and orgies. They used a semicircular design, with rows of stone benches rising outward like ripples. This shape wasn't just for seating, it was for acoustics. The curved form allowed sound to travel cleanly. The whisper on stage could be heard dozens of rows away. They didn't have microphones, but they had geometry, and it worked. Some theaters even used architectural tricks to enhance sound reflection and audience focus. The balance of function and form made them spaces of both entertainment and engineering. Greek architects also understood material properties. They used local limestone and marble, not just for appearance, but for its durability and compressive strength. Marble could be polished, cut finely, and withstood the weight of massive structures. They carved with bronze and iron tools, transported stone on rollers, and lifted heavy blocks using cranes and pulleys. Even with limited technology, they achieved astonishing precision. Stone joints were often cut so perfectly that no mortar was needed. Gravity, weight, and fit did the rest. Mathematics guided more than just shape. It shaped the entire worldview. The Greeks believed in the golden ratio, a proportion where the ratio of the whole to the larger part is the same as the ratio of the larger part to the smaller, roughly 1.618 to 1. They saw this ratio in nature, in shells, leaves, and animals, and they built it into their temples, altars, and sculptures. To them, the universe had an order, and that order was beautiful. They wanted their buildings to reflect it. Harmony wasn't a decoration, it was the design. Over time, these principles spread. The Romans adopted Greek architecture, adding arches and domes. During the Renaissance, architects studied ancient ruins, reviving proportion and symmetry. In modern times, the influence continues. Museums, banks, courthouses, and universities still borrow from Greek forms. Because deep down, we still respond to the same balance, the same rhythm of line and mass, the same silent language of stone, a language first spoken in the hills of Attica, under open skies. So tonight, as you close your eyes, picture a temple in soft morning light. Its columns stand calmly. Its steps are worn by centuries, and yet it stands firm, silent, precise, because someone long ago knew how weight flows, how shape matters, and how numbers can hold up the heavens. Chapter 10. Philosophy of Invention. Plato, Aristotle, and the logic of tools. Before blueprints, before machines, before wires and wheels, the Greeks asked something deeper. Why do we invent? What is a tool? And how do ideas become action? For the Greeks, invention wasn't just mechanical, it was philosophical. They weren't only trying to build, they were trying to understand. In this chapter we explore not just devices, but the thinking that shaped them, the logic behind design, the meaning behind motion, and how philosophy became the silent engine behind innovation. We begin with Plato. Born in 427 before the Common Era, Plato was not an engineer, he was a thinker. But his ideas shaped how invention was viewed. To Plato, the world we touch and see was only a shadow of something deeper. He called this deeper layer the world of forms. In that world, every object, every table, every tool had a perfect, unchanging blueprint. The real hammer was not the one in your hand. It was the idea of a hammer. What we built on Earth was just an imitation of that ideal form. This might seem abstract, but it mattered, because it meant that every invention, every crafted thing, was a step toward reaching the ideal. Design, then, was not just, it was philosophy in motion. Plato's student, Aristotle, took a more grounded approach. Where Plato looked up to the forms, Aristotle looked down into the workings of the world. He believed that things had purposes, that nature, like tools, was built with goals. This idea is called teleology, from the Greek word telos, meaning end or purpose. Aristotle taught that every object, from a rock to a bird, had four causes. The material cause, what it's made of; the formal cause, its shape or design; the efficient cause, what made it; and the final cause, its purpose. Let's use a simple example. A clay cup. Its material cause is the clay. Its formal cause is its round shape. Its efficient cause is the potter's hands. Its final cause is to hold liquid. To Aristotle, invention meant understanding all four causes. Only then could you truly say you knew what a thing was. This framework shaped how the Greeks designed, why they built, and how they explained the world around them. Tools weren't just objects, they were expressions of purpose. Aristotle also asked, what makes something artificial? To him, a natural thing grows on its own. A tree grows, a rock forms, but a tool requires intention. It is shaped by choice, not by chance. This idea separated nature from technology, and it gave birth to the idea of engineering as a human activity, not just an extension of the natural world. Humans, he said, were unique because we could imagine ends, then build things to reach them. Aristotle even classified tools. He said some tools are inanimate, like hammers and wheels. Others are animate, like animals, or even slaves, whose bodies were used to do work. This classification may sound outdated, but it reflects early attempts to define automation, mechanics, and labor systems. Aristotle imagined a world where tools could move on their own. If every tool, he wrote, could do its own work, if a shuttle could weave or a lyre play itself, then craftsmen would have no need of helpers. This was the dream of self-moving machines, a dream the Greeks were just beginning to touch. Let's now explore the word techne. In Greek, techne means craft or skill. It's where we get the word technology. But for the Greeks, techne wasn't just mechanical know-how. It was a blend of knowledge and action. A potter's hands knew clay, a blacksmith's arms knew iron, a sculptor felt the statue inside the stone. Techne was about doing something well, not just finishing it. It required judgment, experience, and insight. This is different from episteme, which meant pure knowledge, like mathematics or astronomy. To the Greeks, both were valuable, but techne was what turned thought into form. Invention, then, was philosophy applied. When Heron of Alexandria designed his steam-powered devices, he wasn't just playing with toys, he was testing how ideas become machines. When architects designed a temple using harmonic ratios, they were practicing philosophical geometry. When doctors used surgical tools with precision, they were enacting Aristotle's ideas of cause and purpose. All Greek invention, in one way or another, was soaked in philosophy. Even myths reflected these ideas. Consider Daedalus, the legendary inventor. He built the labyrinth, a maze so complex it defied escape. He crafted wings for himself and his son, Icarus, using wax and feathers to defy gravity. Daedalus was more than a myth. He represented the human desire to create, and the risks that come with it. Icarus flew too close to the sun. The wax melted. He fell into the sea. The message: invention is powerful, but it requires wisdom. The Greeks also explored invention in politics. Plato described the ideal state as a kind of machine, with rulers, soldiers, and workers acting in balance. He compared the soul to a chariot, one horse pulling toward desire, another toward reason, with the driver struggling to steer. This metaphor shows how the Greeks saw systems everywhere, in tools, in bodies, in cities, even in the soul. To invent, then, was to participate in cosmic structure. The philosophical schools themselves were tools. The Academy, founded by Plato, was a place to test thoughts like experiments. The Lyceum, founded by Aristotle, was where knowledge was classified, debated, and refined. They asked questions like, what makes something useful? Is usefulness the same as goodness? Can a bad man make a good tool? They debated the ethics of war machines, the role of tools in slavery, and the limits of human power. Even without gears or engines, their minds were building structures, mental machines, blueprints of thought. This way of thinking lasted centuries. Roman engineers, Islamic mathematicians, and European inventors during the Renaissance all absorbed Greek philosophy. They didn't just copy machines, they copied the logic behind them. Leonardo da Vinci, for example, cited both Aristotle and Archimedes in his notes. He didn't just sketch inventions, he asked, what is motion? What is force? Why does a lever work? Because in the end, all invention begins with a question, and the Greeks never stopped asking. So tonight, as you rest, picture a quiet hall in Athens. A young student holds a stick. He draws a circle in the sand. An older man watches and asks, what is its purpose? What moves it? What is it for? The stick may become a compass, or a wheel, or a clock. But first, it was a thought. Chapter 11. Greek Military Engineering, War Machines, Tactics and Defense. Invention is not always born of peace. Sometimes it is forged in fire, under siege, under pressure, under threat. For the ancient Greeks, the need to defend and conquer became a powerful engine of innovation. From the walls of Athens, to the open fields of Sparta, to the fortified cities of the Peloponnese, warfare demanded more than courage. It demanded tools. It demanded machines. Greek military engineering was not as famous as their philosophy, mathematics, or temples. But it was just as advanced. They built walls that resisted earthquakes, bridges that could be assembled in hours, siege engines that hurled stones the size of sheep. They turned geometry into trajectory. They turned bronze into power. They turned invention into war. This chapter is about how they did it, and how those ancient designs still echo in the tools of modern battle. We begin with a weapon that changed everything. The catapult wasn't originally Greek. Its roots trace back to Assyria, and even earlier, but the Greeks refined it, systematized it, made it precise. The earliest Greek catapults used torsion power. This meant twisting ropes, often made of sinew or hair, to store energy. Arms were pulled back against this force. When released, they snapped forward, launching a bolt or stone across great distance. This was not wildfire power, it was measured, calculated. Greek engineers used mathematical formulas to optimize tension, length, and angle. They created entire manuals just for calibrating projectile machines. One famous engineer was Philo of Byzantium. In the 3rd century before the Common Era, he described different siege engines, including ballistas which launched large darts, and palintons which hurled stones. He documented the ideal angles for launch, the ratios between arm length and torsion force, the ideal balance of weight, distance, and elevation. For example, Philo wrote that the ideal angle of projection for maximum range was 45 degrees, a finding still relevant in modern physics. Instead of symbols, he used words. He said, when the angle between the launching arm and the ground is halfway between vertical and horizontal, the flight will be farthest. This was science under pressure, mathematics made urgent. Greek cities also invested heavily in defensive architecture. City walls were not just barriers, they were platforms for battle. Walls were built with alternating layers of stone and earth to absorb impact. Towers were placed at regular intervals, allowing defenders to fire in overlapping arcs. Some cities used re-entrant angles, walls that bent inward to trap invaders in crossfire. Gates were reinforced with stone tunnels. Some had double doors, others had kill zones, areas where enemies could be trapped and attacked from above. These were not primitive defenses, they were smart, layered, and deadly. And they kept evolving. In the siege of Syracuse, the brilliance of Greek military engineering was put on full display. The Roman Republic, eager to take the city, laid siege in 214 before the Common Era. But inside Syracuse was a man who would change the story, Archimedes. Using his knowledge of levers, pulleys, and geometry, Archimedes built machines to resist the siege. He designed cranes that lifted Roman ships from the water, and dropped them back in. He created mirrored devices that concentrated sunlight, possibly setting sails aflame from a distance. And he built giant catapults that could fire stones of varying sizes, allowing rapid adjustment during battle. Archimedes didn't just defend, he adapted. He turned mathematics into military advantage. Greek armies also developed tools for mobility. They built portable bridges using modular beams. Engineers could span small rivers or gaps in a matter of hours. They used paved ramps to push siege towers uphill, and they built battering rams covered in hides soaked in water to resist fire. Siege towers had wheels. Some had ladders inside, some even had platforms for archers, turning them into moving fortresses. The coordination needed to operate them was enormous. This was not random force. This was orchestrated engineering. The Greeks also used simple tools with advanced thinking. Take the charobalistra, a type of handheld ballista. It resembled a large crossbow, but used torsion springs and iron arms. It could fire bolts with extreme force and accuracy. It was light enough to carry, powerful enough to penetrate armor, and easy to reload in trained hands. Tools like these gave Greek armies a tactical edge in open combat. Small machines, big results. Another key innovation was in naval warfare. The Greek trireme, a fast, agile warship with 3 rows of oars, was a masterpiece of design. It could ram enemy ships with a bronze-plated prow. It could turn quickly, and it could hold dozens of marines. Triremes were more than ships. They were floating weapons platforms. Greek naval battles were often decided not by who had more soldiers, but by who had better ship design. The Athenians invested heavily in shipyards. Naval innovation was tied to political power. Without triremes, there would be no Athenian empire. Greek military engineers didn't just build, they planned. They used topography to their advantage, built camps near water sources, designed marching orders that included portable supplies. They used terrain models, small-scale versions of battlefields to plan campaigns. This wasn't only about force, it was about foresight. Just like philosophers asked, "What is a good life?" Engineers asked, "What is a winnable war?" And they answered it with wood, stone, rope, and fire. The legacy of Greek military engineering carried forward. The Romans copied Greek siege engines, improving and mass-producing them. Byzantine engineers used Greek fire, a chemical weapon that could burn even on water. And later, in medieval Europe, the principles of catapults, ramps, and towers were studied and revived. Even today, modern engineers learn from the balance, proportion, and logic the Greeks applied under the pressure of war. They remind us that invention does not stop at peace, and design does not end at beauty. Sometimes it marches to the sound of drums. So tonight, as you rest, picture a quiet battlefield, still and grey before dawn. A crew gathers around a wooden frame. They twist ropes, check angles, ready a stone the size of a melon. There are no speeches, no shouting, only geometry and silence. Then release. The stone arcs through the sky. High, precise, inevitable. A machine speaks. In the language of force. Chapter 12. Mapping the Heavens. The astronomers of ancient Greece. When night fell over ancient Greece, the sky became a map. Not of roads or cities, but of time, motion, and wonder. Stars traced perfect paths. Planets wandered like curious messengers. The moon waxed and waned in silence. And the sun, it returned each morning with mathematical grace. To the Greeks, the heavens were not chaos. They were order. They were knowable. They believed if they could understand the sky, they could understand the universe. And so, they began to measure, to observe, to calculate. This is the story of how the ancient Greeks mapped the heavens. Astronomy for the Greeks was not just for farmers or sailors. It was philosophy, it was mathematics, it was religion, logic, and curiosity, all tied to the same stars. The word astronomy comes from the Greek astro, meaning star, and nomos, meaning law, the law of the stars. To them, the sky was governed by rules, and they were determined to find them. The earliest Greek thinkers looked at the night sky and saw patterns. They noticed that some stars never moved. They were always in the same position, turning slowly around a fixed point. These became known as the fixed stars, grouped into constellations, but 5 others behaved differently. They wandered across the background stars. The Greeks called them planetae, meaning wanderers. Today, we call them planets. Venus, Mars, Jupiter, Saturn, and Mercury. The philosopher Thales of Miletus, living around 600 before the Common Era, is considered one of the first to propose that natural laws could explain celestial motion. He predicted a solar eclipse, and that shocked the ancient world. It was no longer just divine will, it was calculable. This opened a new door, from myth to measurement, from prophecy to prediction. Next came Anaximander, who suggested that Earth was a cylinder, suspended in space, floating freely, a radical idea that Earth did not need support. It challenged the old notion that the heavens rested on some invisible pedestal. It suggested that the cosmos was a system, not a stage. Later thinkers would refine that vision and correct its shape, but the seed had been planted. Then came Pythagoras. He saw mathematics not just as a tool, but as the language of the universe. He believed the stars and planets moved in harmony with numbers. He even imagined that celestial bodies created a kind of silent music, what he called the music of the spheres. Not music in sound, but in proportion. The distances, speeds, and orbits all related like notes in a scale. It was poetic, but it pointed toward a powerful idea that mathematical relationships underlie the cosmos. A turning point came with Eudoxus of Cnidus. Around the 4th century before the Common Era, Eudoxus tried to explain planetary motion using a system of concentric spheres. Each planet was attached to invisible, rotating spheres. These nested spheres moved in different directions, creating complex paths. This model didn't fully match observation, but it was the first real mechanical model of the cosmos, an attempt to explain motion using structure. It set the stage for more sophisticated models to come. And then came Aristotle. He adopted the idea of concentric spheres, but added new layers of thought. He believed the Earth was a sphere at the center of the universe. Around it moved the moon, sun, and stars, all embedded in perfect crystalline spheres. This was known as the geocentric model. The idea that everything revolves around Earth, it would dominate Western thought for nearly 2,000 years. And even though it was later replaced, Aristotle's commitment to logic, cause and form helped astronomy evolve from wonder to science. But the most precise astronomical work came from Hipparchus of Nicaea. Living in the 2nd century before the Common Era, Hipparchus was obsessed with measurement. He used geometry to calculate the distance to the moon. He observed eclipses, he catalogued over 800 stars, and gave them coordinates. He even discovered the phenomenon of precession, the slow wobble in Earth's rotation. He noticed that the position of the stars shifted over centuries. This was proof that the heavens were not fixed after all. They changed, slowly, but measurably. Perhaps the most famous astronomer of ancient Greece was Claudius Ptolemy. He lived in Alexandria in the 2nd century of the Common Era and wrote a monumental book called the Almagest. In it, he presented a complete model of the cosmos, Earth at the center, planets orbiting in epicycles, small loops within bigger circles. This system was incredibly complex, but it predicted planetary positions with surprising accuracy. It became the standard model for over 1,000 years. Even though it was wrong in structure, it was right in precision. And it shaped generations of astronomers from the Islamic Golden Age to Copernicus. Greek astronomy wasn't just theoretical, it was practical. Sailors used star charts to navigate, farmers used solar calendars to plant and harvest. Temples were aligned with the sun's position at solstices and equinoxes. Astronomers built instruments, like the astrolabe, which could measure the altitude of stars. This device combined math and mechanics, and became a standard tool across the Mediterranean. The sky was not distant, it was part of life. And then, there was the Antikythera Mechanism, recovered from a shipwreck off the coast of Greece. This device shocked historians, dated to the 2nd century before the Common Era. It was a mechanical computer, made of bronze gears. It could predict eclipses, track lunar phases, model the motion of planets. It had over 30 gears, some with complex non-circular teeth, all hand-cut, all precise. This was not a toy, it was a cosmic calculator. And for centuries it was lost to time. Only now are we beginning to understand how advanced it truly was. What made Greek astronomy special was not just its accuracy, but its spirit. It was based on observation, but guided by reason. It welcomed hypothesis, but tested those ideas against the movement of real stars. It connected the heavens to the earth, not through myth, but through math. The tools were simple: eyes, hands, string, and stone. But the questions were vast. What moves the sun? Why do planets loop backward? Where does the moon go when it disappears? In every answer, they sought pattern, they sought beauty. The legacy of Greek astronomy is enormous. Their methods inspired Islamic scholars who translated, improved, and preserved ancient texts. Their models influenced Renaissance thinkers who challenged them and built new ones. Their tools and terms still remain. Words like planet, cosmos, and astrolabe come from Greek roots. But perhaps their greatest gift was the belief that the universe could be understood, that above our heads was not just mystery, but structure. And with patience, we could find it. So tonight, as you close your eyes, imagine an ancient hillside under starlight. A young astronomer holds a bronze disc. He adjusts a pointer. He watches the moon rise over a distant hill. No telescope, no electricity, just eyes, stars, and thought. And in that moment, he is not lost. He is mapping the heavens. Chapter 13. The Invention of Proof. Euclid, Logic, and Mathematical Certainty. To measure the earth is one thing. To chart the stars is another. But to prove a truth, to know that it is always true, in every place, at every time, that is something deeper. And that was the gift of the Greeks. Not just discovery, but demonstration. Not just observation, but proof. In this chapter, we explore how the ancient Greeks invented the very idea of mathematical certainty, how they moved from counting pebbles to writing the foundations of modern logic. Our journey begins in the Egyptian city of Alexandria, founded by Alexander the Great, home to the greatest library the ancient world had ever known. It was here, around 300 before the Common Era, that a man named Euclid began to teach. Little is known of his life, but his work has echoed through centuries. His most famous creation? A book, a quiet, careful book, called simply The Elements. But don't be fooled by its name. This was no casual writing. It would become the most influential math textbook in all of history. Used for over 2,000 years, studied by Galileo, Newton, and Einstein. And it begins with only 5 assumptions. These 5 assumptions were called postulates. Euclid didn't start with opinions. He started with agreements, things so obvious no one would dispute them. Like, a straight line can be drawn between any 2 points, or all right angles are equal. From these 5 ideas, he began to build, one step at a time, one line, one point, one angle. Each new statement had to follow from what came before. If it didn't follow, it wasn't accepted. This was the beginning of formal proof. Let's imagine a simple case. Euclid begins with 2 points. He draws a line, he then adds a 3rd point, and creates a triangle. He shows that the interior angles of that triangle always add up to a specific total. He doesn't say it's true because he saw it. He shows why it must be true, because of what we already agreed on. This is not trial and error. It is reason. A chain of thought where each link must be solid. A structure of truth, built one theorem at a time. The Elements was not just about shapes. It included arithmetic, ratios, number theory, and geometry. It included over 400 propositions, each one proven carefully. One of them was the famous Pythagorean theorem. It said, in a right-angled triangle, the square of the longest side is equal to the sum of the squares of the other 2 sides. But Euclid didn't just state it, he proved it, using only his postulates and earlier theorems. Each proof was like a staircase, and each step had to hold weight. No leaps, no guesses, only logic. Why does this matter? Because it taught the world that knowledge could be built with certainty, not just believed, but verified. Mathematics became more than a tool, it became a structure. And this structure wasn't held up by authority, it was held up by reason. If you disagreed with a proof, you could test it. Check every step. argue from first principles. This is the heart of scientific thinking, and it started with people like Euclid. Other Greeks expanded this idea. Aristotle, for example, studied logic not just in numbers, but in words. He created syllogisms, statements that followed a pattern of deduction. Like all men are mortal, Socrates is a man, therefore Socrates is mortal. He showed that truth can be preserved by form, not just content. If the form was valid, the conclusion was valid. This became the foundation of formal logic, and it tied directly to how Greeks proved their theorems. Logic and math became siblings. Another thinker, Apollonius of Perga, studied conic sections, the curves made when slicing a cone. He gave us the names circle, ellipse, parabola, and hyperbola. But he didn't just draw them, he proved their properties using definitions and logical sequences. He showed that their behavior could be predicted without ever seeing them. This was pure thought, a kind of abstract geometry that would later be used in optics, astronomy, and eventually in spaceflight. From simple shapes to planetary orbits, it began here. The Greeks also proved things about numbers. Eratosthenes, for example, created a method to find prime numbers called the sieve of Eratosthenes. He didn't list primes randomly. He used pattern and elimination. Another, Euclid again, proved that there are infinitely many primes. How? He imagined a list of known primes, then he multiplied them all together and added 1. This new number was either prime itself or divisible by a prime not on the list, so the list could never end. A powerful idea, proven not by counting, but by logic. Greek mathematicians didn't only use numbers, they also used letters as symbols for quantities and general cases. This allowed them to reason about patterns that applied to any number or shape. They moved beyond the specific to the universal. They explored properties of even and odd, ratios that could not be written as fractions, and lengths that defied exact expression. These were called irrational numbers, discovered by the Pythagoreans, and though it disturbed them, they didn't hide it. They proved it, and kept going. Greek proof wasn't always easy. Sometimes it took years to settle a question, but that was the point. The goal was not speed. It was truth, and once something was proven, it could be passed down, generation after generation. You didn't have to rediscover, you could inherit certainty, a library of logic, a blueprint of knowledge. And it began with a compass, a straight edge, and a mind unafraid to question. The influence of Greek proof is everywhere. In computer science, we write algorithms that follow step-by-step logic, just like Euclid's theorems. In physics, we derive equations from first principles, just like Aristotle's syllogisms. In education, geometry is still taught the way Euclid taught it. Even when we do experiments, we still look for proof behind the results. We ask, why does this happen? Can it be repeated? Can it be derived? We don't just guess, we prove. So tonight, as you drift towards sleep, picture an ancient desk in a stone room. A candle flickers. A teacher draws a triangle in sand. The student watches closely. The teacher does not say, "This is true because I say so." He says, "This is true because of this, and this, and this, and this." And the student nods, because he sees the truth in the pattern, in the reason. Chapter 14. Mechanics and Materials. The Physics of Ancient Construction. Stone by stone, block by block, the ancient world rose from the earth. Temples stood without mortar, columns reached toward the sky, bridges spanned rivers with no steel, and amphitheaters echoed sound without speakers. The Greeks were not just dreamers, they were builders. They understood material, weight, resistance, and balance. They had no computers, no cranes, but they mastered the physics of reality. In this chapter, we explore how ancient Greek thinkers used mechanics and materials to shape the physical world around them. From levers and pulleys to marble and bronze, from architecture to machines. This is the science of construction. We begin with the most essential tool of all, the lever. A simple beam, a single point, but with it, a human could lift a boulder. The principle of the lever was known to builders for centuries, but it was Archimedes who gave it form, logic, and power. He said, "Give me a place to stand, and I will move the earth." He wasn't being poetic, he was being precise. The lever works on a simple rule. If you apply force at a distance, You multiply that force. Imagine a seesaw, on one side, a heavy stone, on the other, a long wooden beam, with a worker pushing at the end. The longer the beam, the easier the lift. Archimedes showed that the force multiplied was equal to the length of the beam on one side, divided by the length on the other. In plain words, double the distance, half the effort. This idea transformed lifting, building, and even warfare. Next came the pulley, a rope over a wheel. Simple, elegant, powerful. Archimedes didn't invent the pulley, but he perfected its use. He designed compound pulley systems that let a single worker lift many times their own weight. In these systems, the rope winds through multiple wheels. Each wheel changes the direction of force and shares the load. The more pulleys, the less force required. This is called a mechanical advantage, and the Greeks understood it well. Pulleys and levers formed the basis of Greek cranes. These were wooden towers with turning arms, ropes, weights, and wheels, cranes. The Greeks could lift marble blocks weighing several tons. They used them to construct temples, statues, and city walls. They also invented the capstan, a rotating device used to wind ropes. It allowed many workers to pull together in perfect rhythm, multiplying their strength. With tools like these, they didn't need brute force. They used balance and design. Greek builders also understood center of gravity. They knew that to balance a heavy object, you had to know its true center. They used this knowledge to place statues upright and position beams with stability. They could estimate weight distribution by feel, by shape, and by trial. They didn't have digital scales, but they had the mind of a physicist. Intuition, guided by philosophy. Let's turn now to materials. The Greeks used what nature gave them, but they did not use it blindly. They understood that stone had different kinds, that wood behaved differently in tension than in compression, that bronze could be cast, hammered, and cooled. They learned which stones absorbed sound, which resisted weather, which cracked under pressure. Marble, for instance, was prized for its beauty and polish, but also for its fine grain and workability. Granite was stronger, but harder to carve. They chose based on need, not just appearance. Wood was another key material for frames, roofs, ships, and machines. They used cedar, oak, and cypress, each with unique qualities. Oak was strong and heavy. Cedar was lighter and more resistant to rot. They seasoned the wood, let it dry, cut it with the grain. They used wooden pegs instead of nails, so joints could expand and contract without breaking. This understanding let them build ships that stayed watertight for years. The Greeks also used metal. Bronze was their favorite. A mix of copper and tin. They melted it in clay furnaces, poured it into molds, then polished and hardened it. Bronze was used for armor, statues, tools, and gears. It was hard enough to cut stone, but soft enough to shape. They understood cooling times. They knew how to remelt scrap. They adjusted mixtures to get different hardness. This was not primitive metallurgy. This was early material science. In architecture, the Greeks also pioneered the column. Not just for beauty, but for load distribution. They created 3 styles: Doric, Ionic, and Corinthian, each with a different thickness, height, and decorative form, but all shared one principle: vertical support with minimal material. They understood compression. They knew that a vertical shaft could bear enormous weight if properly aligned. Many of these columns still stand, after 2,000 years. They also mastered the architrave, the beam that spans the top of columns. Unlike Roman arches, Greek structures used post and lintel designs, which meant heavy beams placed horizontally to prevent sagging. They used entasis, a slight curve in the column that created the illusion of straightness. Even their imperfections were carefully designed. They knew human vision bends straight lines, so they bent their architecture to compensate. Not only engineers, but optical scientists. The Greeks also understood acoustics. Their amphitheaters were shaped to carry sound from stage to seat, even in the back row. They used rows of stone seats arranged in semicircles. They placed reflecting surfaces behind the actors. They knew sound bounced. They knew shape mattered. Modern engineers have studied these theaters and still find them remarkable, with no microphones, no speakers, only stone and air. The Greeks built spaces where every word could be heard. This is physics in architecture. One of the most advanced uses of mechanics was the odometer. It measured distance traveled by a cart. Using gears connected to the wheel, the device dropped a small stone for each unit of distance. At the end of a journey, you could count the stones and know how far you had gone. It was used for road planning, military mapping, and taxation. This was the beginning of mechanical measurement, and it worked because they understood rotation, gear ratios, and counting. Even their temples used mechanics. Some featured doors that opened when fire was lit on the altar. This was done using air pressure. As heat caused air to expand, it moved water between vessels, which moved weights and levers, which opened the door. A chain reaction, invisible motion, cause and effect. It wasn't magic, it was science, in stone and bronze, and it amazed those who witnessed it. The Greeks laid the groundwork for modern civil engineering. They understood stress and strain. They knew how to build on slopes. They used leveling tools with water to keep buildings flat. They invented the dioptra, a surveying instrument that used sight lines and angles. They understood load paths, how weight flows through a structure, and they practiced modularity, designing parts that could be reused, replaced, and scaled. Everything was built with intent. So tonight, as you fall into sleep, picture a quiet workshop, wood shavings on the floor, stone dust in the air. A crane stands in silence. A rope stretches tight. The builder checks the balance, adjusts the angle, then nods. The block lifts, slowly, smoothly, not by force, but by design. Chapter 15, Greek Medicine and Surgical Tools, Healing by Design. In every civilization, people have asked the same questions. What causes illness? What makes the body heal? The answers have not always been clear. Some turned to the gods, some blamed spirits or curses, but the Greeks, they searched for patterns. They watched, they recorded, they began to measure the body as they measured the stars. And through this, they transformed medicine from ritual into reason. Greek medicine was not perfect, but it was organized, structured, systematic. They believed that the human body could be understood. They observed symptoms, tested treatments, and recorded outcomes. They built tools to assist the healer. They trained doctors in ethics and precision. It was the beginning of medicine as a science, and at its heart was one name: Hippocrates. Hippocrates lived around 400 years before the Common Era. He came from the island of Kos, a place known for its physicians. But Hippocrates did something different. He stripped medicine of superstition. He said illness was not punishment, but imbalance. He believed the body had systems, and those systems could go wrong, but also be corrected. He taught that doctors must observe without emotion, and treat without harm. He was calm, methodical, and deeply rational. His most lasting legacy was a small document, the Hippocratic Oath. It stated that physicians must act for the good of the patient, protect privacy, and avoid unnecessary harm. Even today, doctors take a version of this oath before they begin to practice. It was one of the first times ethics entered a profession, not as suggestion, but as duty. Greek medicine, from the very start, was about principle. Hippocrates and his students described the body in detail. They identified organs, documented fevers, classified types of pain. They wrote over 60 medical texts, now called the Hippocratic Corpus. These texts included case studies, surgical procedures, and environmental effects on health. They emphasized diet, exercise, and observation, not just treatment, but prevention. They believed in balance, especially among the four humours. The theory of the four humours became central to Greek medicine. They believed the body contained four fluids: blood, phlegm, yellow bile, and black bile. Health was a balance of these. Sickness came when one was in excess, or when they were poorly mixed. Though incorrect by modern standards, this theory encouraged doctors to think about systems, to seek causes, not just symptoms. It moved medicine closer to science. Greek doctors developed tools to aid their diagnoses and treatments. They used speculums to examine body cavities, long, hollow tubes made from bronze or copper. They crafted forceps to grasp tissue or extract bone fragments. They had scalpels made of iron, sharpened carefully by hand. They also used probes, hooks, and cauterization irons. Tools were sterilized by fire and often cooled in wine or vinegar. This was early antiseptic practice, guided by logic, not yet by germ theory. In surgery, Greek physicians were cautious. They knew the risks, but they attempted procedures that were rare for their time. They treated wounds with bandages soaked in honey, which had natural antibacterial properties. They drained abscesses, removed foreign objects, and aligned fractures. They used splints made from wood or reeds, tied with linen strips soaked in resin. They wrote about concussions, epilepsy, and eye disorders. Each entry described not just what they saw, but what they did. It was practical medicine, rooted in observation. Greek doctors believed in the healing environment. Hospitals as we know them didn't exist, but there were Asclepians. These were healing temples dedicated to Asclepius, the god of medicine. Patients came for rest, clean air, and treatment. They slept in quiet courtyards, bathed in sacred springs, listened to gentle music. While not scientific, these centers promoted recovery through calm and care, a lesson modern hospitals still use today. Greek physicians also believed that the mind affects the body. They noted that fear, sadness, and stress could worsen illness. They observed that comfort, confidence, and hope could improve recovery. They encouraged conversation, rest, and mental clarity. They didn't separate the patient from the person. They treated the whole being, not just the injury. It was medicine with empathy, and it mattered. One notable Greek physician was Galen, though he lived later during the Roman Empire. He was trained in the Greek tradition. He performed animal dissections to understand anatomy. He mapped the nervous system, described the spinal cord, and studied the effects of injuries on motion. Though many of his ideas were later corrected, he left behind thousands of pages of anatomical theory. His writings were studied for over a millennium, passed from Greece to Rome to the Islamic world, and back to Europe during the Renaissance. His legacy was not just in knowledge, but in method. Greek medicine also left its mark on medical terminology. Words like cardiology, neurology, ophthalmology, and diagnosis all come from Greek. They were the first to organize medical language with root words and structure. This helped doctors communicate, train others, and build systems of knowledge. It wasn't just treatment, it was a framework for the science of healing, and it has lasted for over 2,000 years. The Greeks also contributed to pharmacology. They used herbs, minerals, and animal parts to create treatments. They studied effects through trial, observed reactions, adjusted dose. Plants, like willow bark, which contains the basis of aspirin, were used to treat pain. They also used poppy extracts for sleep, garlic for infection, mint for digestion. They recorded combinations, prepared ointments, and shared remedies across regions. Their medicine was not random. It was experimental. So what was the Greek model of healing? It was based on 3 ideas. 1. The body follows patterns. 2. Observation leads to understanding. 3. The physician must first do no harm. May seem simple, but these ideas formed the foundation of modern medicine. Even when wrong about causes, they were often right about method, and that method endures. So tonight, as you rest, picture an ancient clinic under olive trees. The physician checks the patient's pulse. He examines the tongue, listens quietly, then prepares a tincture from nearby herbs. There is no rush, no machines, just time, skill, and presence. The patient closes their eyes, a breeze moves through the leaves, and in that moment, healing begins. Chapter 16. Sacred Proportion. Greek Mathematics in Architecture. To the Greeks, beauty was not just decoration. It was order, it was harmony, it was mathematics. Their buildings were not designed by eye, but by ratio, not just for shelter, but for meaning. They believed the proportions of a temple could reflect the proportions of the cosmos, that a column could echo the rhythm of the body, that a line, drawn well, could touch the divine. This is the story of how ancient Greek architects used mathematics to build a world of balance, rhythm, and grace, a world of sacred proportion. Let us begin with the most famous building in ancient Greece, the Parthenon. It stands on the Acropolis in Athens, built in the 5th century before the Common Era, a temple to Athena, a monument of stone and logic, At first glance, it looks simple. Straight lines, right angles, perfect symmetry. But look closer and you find subtle curves, precise ratios, and masterful corrections for human perception. It was not built just to stand, it was built to resonate. One key principle in Greek architecture was symmetry. Not symmetry as in mirror image, but proportional relationship. Everything from the width of a column to the spacing between beams was based on mathematical ratios. These ratios created visual harmony. They made structures feel balanced, even when parts were unequal. The most important of these ratios was the golden ratio. The golden ratio is the relationship where a longer length divided by a shorter length equals the total length divided by the longer length. In plain words, if the short side is 1, the long side is approximately 1.618. This creates a shape that repeats in nature, in leaves, shells, and even galaxies. The Greeks called it divine proportion. They used it in sculptures, columns, and facades. It made buildings feel natural, and somehow inevitable. Not forced, but found. In the Parthenon, this ratio appears again and again, in the height of the facade compared to its width, in the spacing of the columns compared to their height. Even the sculpture panels called metopes follow this ratio in height to width. It was not accidental, it was designed, a temple made of number, a prayer in stone, and it worked. People still feel its beauty, even without knowing why. The Greeks also used mathematics to correct visual distortions. Straight lines, when seen from far away, appear to curve. Columns, when placed perfectly parallel, can seem to lean inward. The Greeks anticipated this, and they compensate. The Parthenon's columns are slightly thicker in the middle. This is called entasis. It corrects the illusion of thinness that occurs when long columns rise straight. The base of the Parthenon is not flat. It gently arches upward in the center. This keeps the lines looking straight to the human eye. These are optical refinements, done without machines, only with geometry and intuition. Greek architects didn't just design temples, they built theaters, stadiums, homes, and agoras, all with attention to form and function. Theaters like the one at Epidaurus were shaped in semicircles. Each row followed a perfect arc. This preserved acoustics, so even a whisper on stage could be heard clearly in the back row. They used radial symmetry, equal spacing, and gradual elevation. Again, it was not art alone, it was applied geometry, an architecture of experience, designed to serve the senses, and guided by number. They also understood modular design. Instead of measuring in feet or cubits, they used a system based on units derived from the building itself. For example, the column diameter might be used as a base unit. Every other measurement, spacing, height, depth, would be expressed as a multiple of that unit. This made scaling easier. Temples of different sizes could follow the same rules. It was a relative system, consistent, flexible, elegant, and it kept portions intact, no matter the scale. The use of orders in columns also reflected mathematical thinking. There were three main orders: Doric, Ionic, and Corinthian. Doric columns were the simplest, thick, fluted, and without base, used for strength and solidity. Ionic columns were more slender, with scroll-like capitals. Corinthian columns were the most ornate, topped with carved leaves, but beyond style. Each order followed strict proportions: column height to width, base to shaft, spacing to entablature. Everything was regulated by number. It gave architecture a language of rules, a grammar of stone. They also mastered triangulation. Roofs required weight distribution. The triangular pediment allowed the load to spread evenly to the columns. Beams were laid using the principles of compression. Materials were chosen for tensile strength. Even in large open spaces, they preserved stability without internal supports. This was pure mechanics, guided by math. It allowed for monumental scale without chaos, form following function, but both governed by ratio. We must also speak of Vitruvius. Though he lived in Roman times, he echoed Greek principles. He believed a building must have three qualities: firmitas, firmness; utilitas, function; vimestus, beauty. And all three, could be guided by mathematics. He studied Greek temples, praised their harmony, copied their ratios. In this way, Greek architecture lived on, long past its stones. It became the model for Renaissance art, Enlightenment science, and even modern design. One of the most iconic examples of math in Greek design was the Delium problem. A legend says the gods asked the Greeks to double the volume of a cube as an offering, but it could not be done using only compass and straight edge. This led to centuries of exploration in geometry. Even if the problem wasn't solvable in that form, it forced thinkers to push the boundaries of construction and logic. It was a challenge, and challenges inspired invention. Mathematics as motivation. The Greeks didn't separate art and science. They used one to elevate the other. Beauty was not decoration, it was evidence of order. If something looked right, felt right, held weight, and repeated natural ratios, then it was beautiful. Not because it pleased the eye, but because it pleased the mind. Form aligned with principle, and when they walked beneath those columns, or gazed at those ceilings, they weren't just admiring the view, they were admiring the math behind it. So tonight, as your eyes begin to close, picture a quiet construction site under moonlight. Stone blocks rest in rows. A single line is drawn across the foundation. Two builders check the angle. One nods. They are not rushing. They are aligning the world to something larger than themselves. A proportion, a rhythm, a sacred rule. And with each measured cut, each balanced beam, they build not just shelter, but a philosophy. Chapter 17, Predicting the Wind, Weather Instruments and Climate Science in Ancient Greece. The sky is not silent. The wind moves with purpose. The clouds gather in patterns. And the Greeks listen. Before satellites, before Doppler radar, before barometers and thermometers, the ancient Greeks were already trying to understand the weather, not just to survive it, but to predict it, because weather shaped every part of their lives, their harvests, their sailing, their wars, and their trade. So they watched, they measured, they guessed, and over time, they began to know. Greek thinkers approached weather the same way they approached everything else, through observation, pattern, and reason. They weren't content with saying, "It rains when the gods are angry." They asked, "Why does wind change direction? Why do certain clouds bring storms? What makes air feel heavy?" This curiosity led to some of the earliest meteorological instruments in recorded history. And in this chapter, we explore those tools, those theories, and those bold first steps toward the science of climate. Let us begin with the most iconic, the Tower of the Winds. In Athens, near the Roman Agora, stands an octagonal marble tower, built in the 1st century before the Common Era. Each face of the tower represents a different wind direction, carved as a figure, a godlike being blowing air across the stone. This tower was more than sculpture. It was a multifunctional weather station. On its roof was a weather vane, one of the first in recorded history. It turned with the wind, pointing to the god who represented that direction. In essence, it was a symbolic and scientific compass. Inside the tower was something even more sophisticated, a water clock or klepstra. This device measured time using the steady flow of water from one container to another. It allowed people to track the hours, even on cloudy days or at night. It was powered by a spring and required precise regulation of flow. The combination of wind direction on the outside and time measurement inside showed how deeply the Greeks wove climate and calculation together. They didn't separate air and time, they saw the sky as a system. Another key thinker was Anaximenes. Living in the 6th century before the Common Era, he proposed that air, not water, was the fundamental element. He observed that compressed air becomes colder, that expanded air becomes warmer. He used his breath, his own mouth, as a kind of testing lab. When you blow air with lips opened, it feels warm. When you narrow your mouth, it feels cool. He theorized that this change was due to density. This was an early insight into thermodynamics, without equations, just breath. And the philosopher Aristotle took weather study even further. He wrote a book called Meteorologica, one of the first systematic texts on climate and sky phenomena. He described evaporation, condensation, dew, frost, and snow. He talked about rainbows, halos around the moon, and the phases of the moon itself. He didn't get everything right, but his curiosity was relentless. He believed the heavens obeyed natural laws, not divine whims. And this belief changed everything. In Meteorologica, Aristotle explained weather using the four elements: earth, air, fire, and water. He believed air could rise, condense, and fall as rain. He described thunder as the sound of clouds colliding, lightning as dry, hot vapor being released. His explanations were imperfect, but they were attempts to build models, to connect what is seen with what is understood. He moved beyond stories. He searched for systems. Another important figure was Theophrastus, a student of Aristotle. He wrote the Book of Signs, a collection of weather observations. He studied animal behavior before storms, cloud shapes, changes in wind direction. His goal was prediction, to tell in advance what the sky would bring. He made a kind of weather manual for sailors, farmers, and travelers. He didn't build devices, but he built a framework. He helped make forecasting possible, not through technology, but through pattern recognition. The Greeks also invented early anemometers, devices for measuring wind speed and force. They used wind vanes and banners, mounted on tall poles. By observing the angle or flutter of fabric, they could infer how fast the wind blew. These were qualitative, not quantitative, but they were still tools. Over time, they correlated wind strength with sea conditions, travel times, and the outcome of naval battles. Sailors especially became experts in reading the wind, not by equations, but by experience. Some early thinkers also created instruments to measure humidity. One simple device used a sponge or wool exposed to the air. The weight was checked regularly. If it grew heavier, it meant more moisture in the air. This allowed some early predictions of rain or fog. Again, no electronics, no calibration tools, just materials, observation, and logic. Science, in the quietest forms. The Greeks understood the importance of climate zones. They divided the world into regions based on sun angle and weather patterns. They noticed that in Egypt, the sky was always clear. In northern lands, it rained more often. They classified areas as torrid, temperate, or frigid. This understanding influenced travel, trade routes, and even theories of government and personality. They believed weather shaped culture, that climate influenced thought. It wasn't always accurate, but it showed a willingness to connect sky and society. In navigation, the Greeks were ahead of their time. They used windroses, circular diagrams that showed principal wind directions. These helped sailors plan routes. They learned which winds came in which months. The Etesian winds, for example, strong summer breezes from the north, were critical to sailing back from Egypt. Sailors didn't just hope for wind, they studied it, and by doing so, they made the Aegean their highway. No GPS, no forecasts, only the stars, the air, and memory. Greek doctors also noticed that health changed with the weather. The Hippocratic text, Airs, Waters, Places, explores how climate affects the body. It recommends different treatments depending on wind, temperature, and season. It describes diseases that appear only in spring or worsen in autumn. This is early environmental medicine. They didn't know about bacteria, but they knew the body and the sky were connected. Their hospitals were built in airy places. Their recovery centers faced the east. Why does this matter? Because it shows that science does not begin with technology. It begins with attention. The Greeks had no satellites, no sensors, no computer models, but they had sky and time and questions. And that was enough. They built theories, wrote observations, invented instruments, and created the first human attempt to read the weather with reason. They didn't always get it right, but they began the conversation, and we are still answering it today. So tonight, as the wind rustles outside your window, imagine an old tower in marble and stone. A sculpted figure turns gently, pointing toward the breeze. Inside, water drips, measuring the hour. Scholar records the cloud shape, marks the date, nods thoughtfully, not with certainty, but with care. He's not controlling the weather, he's simply trying to understand it. Chapter 18. The Antikythera Mechanism. The first analog computer. So it holds secrets, and sometimes it gives them back. In the year 1901, a group of sponge divers, exploring the coast of a small Greek island, found something unexpected. Not a statue, Not a coin, not a scroll, but something stranger. A lump of bronze, corroded, fragmented, covered in gears, was pulled from a shipwreck near Antikythera, and it would become one of the greatest puzzles in the history of science. A machine, 2,000 years old, built by hands that understood the sky. This is the story of the Antikythera Mechanism, the world's first known analog computer. At first, no one knew what it was. It didn't look like anything, just twisted green metal and decayed wood. It sat in storage for years, ignored, until someone noticed something strange. Gears, dozens of them. Teeth interlocking, aligned with care. And slowly, the mystery began to unfold. This wasn't junk, it was engineering. With X-rays, researchers uncovered a complex system of rotating dials and inscribed scales. Inside the fragments were at least 37 bronze gears, carefully cut and mounted on shafts. Some rotated forward, others backward. The whole device could be turned with a single hand crank. It didn't just move, it calculated. It was a mechanical model of the cosmos. Scholars believe the Antikythera Mechanism was built around 50 BC. It was likely housed in a wooden box, about the size of a shoebox. On the front, dials that track the position of the sun and moon through the zodiac. On the back, other dials for lunar cycles, eclipses, and calendar. One dial showed the Metonic cycle, a period of 19 solar years that almost exactly equals 235 lunar months. Another dial tracked the Saros cycle, a period of 18 years used to predict eclipses. This wasn't fortune-telling, it was astronomy in metal. Let's take a moment to understand what these gears were doing. Imagine you turn the crank once. Inside, gear teeth catch and spin other gears. Some rotate quickly, others slowly. Each one mimics a celestial motion. One full turn might represent a day, or a month, or a full year. The gears multiply, divide, reverse. Their ratios carefully chosen translate time into position. This is mechanical calculation, and it's happening in the 2nd century BCE. Let's talk about some of these ratios. One important gear pairing has a ratio of 202:3 to 19. That's not random. It encodes the Saros eclipse cycle. Another pairing matches the Metonic cycle using a gear ratio of 204 to 19. These are not guesses, they're accurate, mathematically sound. Someone designed this with precision tools, a deep understanding of astronomy, and a masterful hand. It's like finding a smartphone inside a Roman ruin. We don't know the original maker's name, but we know they were likely influenced by the work of Hipparchus. He was a Greek astronomer who lived around 50 BCE. He discovered precession, the slow wobble of Earth's rotational axis. He refined models for lunar and solar movement, and he may have even written a guide for making such a device. The Antikythera Mechanism seems to encode his math, including the epicycles, small circular motions that explained how planets appeared to move backward. Not accurate by modern standards, but brilliant for its time. The craftsmanship is staggering. Gear teeth were cut with triangular precision, axes aligned, scales inscribed by hand. Some components are only a millimeter thick. The engravings, tiny Greek letters, sharp, even after 2 millennia. This wasn't amateur work. It required advanced metalworking, knowledge of gear mechanics, and an understanding of planetary cycles. This was a scientific instrument, built to model time itself. One of the most mysterious parts is the eclipse prediction dial. It doesn't just track eclipses, it predicts type and timing, solar or lunar, partial or total. Some researchers believe it also included a mechanism for color-coding eclipses, perhaps to indicate their visibility or intensity. Think about that, a 2,000-year-old device that could tell you when the next eclipse would happen. It may even have included textual prompts, short inscriptions describing what to expect. There's also evidence that the device tracked the Olympic Games. One dial appears to follow a 4-year cycle, matching the timing of ancient athletic competitions. This suggests the mechanism blended science with culture and ritual. It wasn't just for scholars, it was meant for people, to show that the sky was knowable, predictable, human-scaled. The divine rendered mechanical. But how was it used? Most likely, it was used for education and demonstration. perhaps in a school, perhaps by a wealthy patron, or a traveling astronomer. It would have shown people, visually, mechanically, how the heavens moved. It turned abstract cycles into something you could see and feel, and by doing so, it brought the sky closer. It turned time into touch. We now know of at least 82 fragments of the original device. Many are tiny, some only a few centimeters across, but researchers have used 3D X-ray imaging to reconstruct the inner layout. Modern replicas have been built, showing exactly how it might have moved. It would have taken weeks or months to make, by hand, with tools lost to time, and yet it worked. A computer before there were computers. What makes the Antikythera Mechanism so extraordinary is not just its complexity, but its isolation. No other device like it has been found from that era. Its design vanishes from history for over 1,000 years. Not until the medieval Islamic world, and later, Renaissance Europe, do we see anything remotely comparable. It's as if someone discovered an entire branch of science, built a masterpiece, and then the knowledge disappeared, buried in salt and silence. What happened? Some think it was too advanced, too expensive, too fragile. Others believe wars and empire shifts destroyed the schools that taught its making. Perhaps the skill was passed by word of mouth, lost when a few key minds were lost. We may never know, but what we do know is that for one brief moment, in one brilliant workshop, it was real. The sky in gears. So tonight, as you rest, imagine a quiet chamber lit by oil lamps. A craftsman leans over a bronze plate. He files a gear tooth, checks the spacing, mounts it to a spindle. Slowly, the machine takes shape. A ring for the moon, a wheel for the sun, a hand that points to eclipses yet to come. No magic, no superstition, just design. Chapter 19. Roads, aqueducts, and infrastructure. The blueprint of civilization. Civilization is not only built by ideas, but by infrastructure. Without roads, ideas cannot travel. Without water, cities cannot grow. The greatness of ancient Greece was not just in philosophy or art, it was also in stone, clay, and movement. This chapter is about those things that lie beneath the glory: the roads, the aqueducts, the systems, the unseen inventions that made Greek civilization possible. Let us begin with the roads. Ancient Greece was a land of mountains, valleys, and islands. Travel was difficult, transport was slow, yet they built a network of stone-paved roads that connected cities, ports, and sacred sites. These roads weren't just paths, they were carefully engineered layers of gravel, sand, and flat stone. They resisted erosion, they drained water efficiently, and they allowed for the movement of armies, goods, and information. Greece, in effect, was made walkable. One of the earliest examples of Greek infrastructure comes from Knossos on the island of Crete, the Minoan civilization, which predates classical Greece by over 1,000 years, built roads with stone curbs, raised surfaces, and even drainage channels. They were not simple tracks. They were the first true roadways in Europe. Some were as wide as 4 meters, and they connected palaces, towns, and ports with surprising precision. Even at that early stage, the idea of structured movement was already in place. By the classical period, Greek engineers had refined road design further. One key example was the Sacred Way, the path between Athens and the sanctuary at Delphi. This road was used by pilgrims, priests, and messengers. It had resting areas, mile markers, and way stations. It wasn't just practical, it was also ritualistic. Travel itself became part of the sacred experience. The road was not just a route, it was a message. The Greeks also built roads for military purposes. The city-state of Sparta, for instance, maintained routes for troop movement and communication. Roads connected border forts, allowing fast deployment of hoplites in case of invasion. Some cities used beacon towers, planted at intervals across high ground, to send messages with fire or smoke. A primitive form of long-distance communication, fast, visual, coordinated. Roads in this context were not only for trade or worship, but for defense. Now let us turn to water. A city cannot survive without it. And the Greeks knew this well. They designed systems to capture, transport, store, and purify water. They built aqueducts, cisterns, fountains, and drainage tunnels. Even on islands with no rivers, They created rain collection systems. Using sloped roofs and underground reservoirs, water was engineered. The most famous Greek water system may be the Tunnel of Eupalanos on the island of Samos. It was built in the 6th century BCE, 1,000 meters long, cut through solid rock from mortix ends simultaneously. They met near the middle with less than a meter of deviation. Think of that, 2 teams, digging in darkness, with no satellite, no GPS, no laser levels, just math. And yet, they met. It was a marvel of surveying, geometry, and courage. The tunnel carried fresh spring water to the city of Samos. Gravity did the work. The engineers used a slight incline, just enough for flow, without stagnation. This principle, called a hydraulic gradient, is still used in modern pipelines. Their materials were simple: terracotta pipes, stone channels, carved basins, but the principles were enduring. Water, managed by design. Greek cities also built public fountains, supplied by aqueducts and underground channels. These were not luxuries. They were essential infrastructure. Women collected water daily. Children played nearby. Elders gathered in shade. The fountains were gathering place civic centers. Water wasn't just necessity. It was community. Its flow regulated by engineers. Its presence felt in daily life. And that, too, was invention. Sanitation mattered as well. In cities like Athens, sewers ran beneath the street. Open channels carried waste out of densely populated areas. They used sloped surfaces, flow direction control, and catch basins for debris. In some cases, public toilets were linked to flowing water channels, continuously flushed. It wasn't perfect, but it was thoughtful, and in that thought, there was health. Greek engineers also mastered the use of materials. They used limestone for structure, clay for pipes and tiles, lead for water joints, and wood for scaffolding and bridges. They calculated load-bearing capacity. They understood erosion. They accounted for freeze-thaw cycles in colder regions. They didn't build by accident. They built with reason, with care, with the mathematics of matter. Even agriculture was supported by infrastructure. They built terraces on hillsides to prevent soil erosion and capture rainfall. They dug canals to bring water from distant springs to fields. They created grain silos, dry storage systems, and food distribution centers. They planned for drought. They planned for surplus. It wasn't just survival, it was stability. And stability made philosophy possible. Greek ports were also feats of engineering. They built harbors with breakwaters to protect against tides and storms. Cities like Piraeus, near Athens, had complex dockyards, warehouses, and secure naval bases. Some ports even had cranes and winches for unloading heavy goods. Trade flourished, fish markets thrived, ideas moved with the tides. Infrastructure was the skeleton of commerce, and commerce was the bloodstream of the polis. So what does this tell us? That the glory of Greece was not only in its temples, but in its tunnels, not only in its sculptures, but in its sewers, not only in the agora, but in the aqueduct. These systems don't always make it into the poems, but they made the poems possible. They supported life, enabled movement, sustained growth, and they still whisper to us from beneath the earth. So tonight, as your breathing slows, picture a quiet stone road in moonlight. Rain slides gently off a curved gutter. A trickle moves toward a distant drain. The city sleeps. Beneath it, tunnels hum with flowing water. A cistern echoes. A pipe drips. Somewhere, a hidden valve turns, and no one hears it, but everything depends on it. Chapter 20. The Legacy of Greek Invention. How Ancient Ideas Still Shape the Modern World. It began with a question. Then came the tools, the temples, the gears, the maps, the fire. And now, thousands of years later, we still live in a world touched by their answers. The legacy of ancient Greek invention is not buried in museums. It's woven into our lives, not as ruins, but as foundations, not as dust, but as structure. From the moment we wake, we engage with Greek thought. The way we measure time, days, months, years, follows patterns they studied. Our clocks use gears, descended from their designs. Our cities rest on infrastructure they pioneered. Our architecture mirrors their symmetry. Our mathematics continues their search. Our science, our philosophy, our civic life, all stand on ancient ground. Think about the roads we drive on, the public water that flows, the layout of cities, divided into grids and districts. These are echoes of what the Greeks developed. Road systems, water tunnels, city planning, with rational symmetry. Even the stadium you pass by, a Greek word, a Greek invention. Even the theatre, the library, the academy, all trace their ancestry to minds that lived 2 millennia ago. But their legacy isn't just physical, it's intellectual. The Greek method was not just to build, but to question, to doubt, to measure, to repeat. This way of thinking became the basis of modern science. They asked, what is light? What is number? What is justice? Not to end the discussion, but to begin it. And we are still in that conversation. Consider mathematics. When a student learns geometry, they're working with principles laid down by Euclid. When we solve equations, we use notation derived from Greek logic. When we plot planets, we refine the model started by Ptolemy and corrected through the centuries. When we talk about atoms, we're using a term coined by Democritus. When we talk about chaos, entropy, or symmetry, we are speaking ancient languages with modern voices. Even the idea of democracy was born in Athens. Imperfect, yes, but revolutionary. Citizens voting, debating, challenging leaders in public forums. This concept traveled from amphitheaters to constitutions, from Greek agoras to global parliaments. Our politics may change, but the architecture of our systems remains deeply Greek. The idea that the people rule. In medicine, the Hippocratic Oath still echoes in hospitals. The focus on observation, cause and effect, patient history, these began with Hippocrates, who taught that health was not magic, but measurable. In biology, Aristotle's system of classification became the groundwork for later taxonomy. His belief in empirical study helped shape the scientific method. Even though some of their theories were wrong, their approach was right. They trusted evidence. They chased consistency. They built the rules. We now refine. And what of engineering? The Antikythera Mechanism, a symbol of what was possible. Its gears live on, in every clock, every gearbox, every mechanical system. Its principles shape everything from planetariums to analog computing. It was not merely a machine, it was a message that models can move, that knowledge can spin. And once set in motion, it never truly stopped. We see echoes of Heron's machines, in vending systems, hydraulic valves, and steam engines. We see the logic of Archimedes in levers, pulleys, and buoyancy testing. We use Greek trigonometry in GPS, architecture, aerospace. Even your phone, with its accelerometer and gyroscope, operates on physical principles first explored in ancient Greece. Modern tools, ancient truths. And then there is the sky, constellations with Greek names, planets with mythological lineage. We still divide the heavens by the zodiac. We still reference equinoxes and solstices by terms they defined. When we launch telescopes, we inherit the vision of those who first tried to predict eclipses with hand-cut gears. When we talk about gravity, we begin with motion, and motion was something the Greeks observed first. Their influence isn't frozen in time, it's adaptive. We modernized it, globalized it, added digital layers. But underneath still lies Greek geometry, Greek mechanics, Greek ethics. Their tools weren't perfect, but their methods were durable. They built a platform not for a single generation, but for centuries to come. They planted questions that still grow. And even in our culture, they are present. The drama we watch, the debates we hear, the Olympics we celebrate, all born in their soil. Their myths shape stories, their language seeds vocabulary, their ruins, even broken, inspire. Because ruins are not dead, they are paused, and every time we look at them with fresh eyes, we continue their work. We are not separate from the Greeks, we are their future. So tonight, as you rest, know this: you are surrounded by echoes. In your calendar, in your power grid, in the angle of your roof, In the way you solve problems, you don't have to visit a museum, just turn on a light, measure a recipe, vote, write, build. The legacy of Greece is not an ancient story. It is still unfolding in you. And now, our journey comes to a close. 20 chapters, 20 doors into the past. We have walked roads, turned gears, measured stars, mapped minds. We have seen that the ancient world was never primitive. It was brilliant, measured, curious, inventive. And everything we are now began with that spark. If this series helped you fall asleep, helped you learn, or helped you wonder, let us know. Tell us where you listened from, and what time it was when your journey began. Thank you for joining us for 3 hours of ancient Greek inventions that still shape our world. The past is never truly past. It's just the beginning. Sleep well, and when you wake, build something new.